hopefully having a good Sunday morning. I loaded up the handout. It's the same thing I emailed out yesterday. Just for what it's worth, I'm going to just avoid anytime I do anything, just dodge the portal. I think it's just easier to upload it through this channel. But if you didn't get it, email me, because I send it out in bulk and sometimes it ends up in spam. So what I sent out was the one for today, but then I also sent out all of my handouts for the OChem lectures, all my handouts for the physics, and all the handouts for GChem lectures. So did anybody not get an email with 4 attachments that just have way too much going on? And if you didn't, email me, because it might have ended up in your spam folder. Okay, so I have a strange question for some of you. For anybody who owns Apple products, is it common that the various Apple products that are all supposedly on the same timing system, you like click automatic timing, have different times? Or is one of my devices just living in the past? Okay, it is weird. I thought, so my phone and my regular computer are on time, but my my iPad's living in the future. So if you want any stock information, you want to know who wins, let me know. It's only, it looks like about half a minute in the future. Yeah, I selected auto timing for all of them. So yeah, I put it on auto select. That's why it's just so strange. And it's been that way since I got it from day one. Yeah, that's probably end up doing it and see what happens. Not that it matters. It's just, I just always look at that and think, that is so random. All right, I'm gonna load the handout one more time. No, that was, okay, I should probably address that. That was my mistake sending out, because when Josh got back from his trip, he called to say, hey, how did it all go? Blah, blah, blah. It's like, okay, first off, you probably should have checked in during, but anyway, he said he was going to email everybody out and explain what happened. I just, again, I turned over reins to let him run the show, but I'm sitting here just, it's just nuts. Long story short, end up the teacher who was supposed to teach yesterday never accepted the job. So, I mean, that's just being as honest and brutal as it could be about it. And I don't know if he emailed. So it's just, I don't know if he's going for a cover, but it will be mopped up. And I don't know if he's waiting to figure out who's going to teach it, or if he's just gun shy, whatever it is. But I don't know how that could be. Yeah, I sit here just dumbfounded. But you know, it is what it is, and it'll get mopped up. But I guess it just she just didn't know. So for what it's worth, hopefully it'll continue. I can't teach bio, no way in hell. I mean, that's not my forte. And so Coy moved into what I teach. So I will do mop up. That is my whole purpose this time, because I owe it to you guys who signed up, but I also want to just eject out. So anyway, I'm going to go ahead and start the lecture. Let me, I'm going to load the handout one more time. So here it is. And Simran, who was supposed to teach, actually, she contracted COVID, and she's legitimately going through something right now. So, I mean, no complaints. Those things happen. But sorry for the change of pace. What it will do is it's going to end up giving an extra outcome lecture. So I'll cover this one. She's going to do a mop-up one to kind of fill some of the stuff we don't get to today, because I want to add a little spectroscopy today because spectroscopy was consolidated. So, and so there'll be an extra lecture. I believe Thursday is what we're talking about. We'll see exactly where it falls in place. Okay. That said, let me go ahead and start. So OChem on the MCAT, just to give you an idea, it pretty much falls into 3 camps. The first one, organic questions about biomolecules. So biorelated things, give you a pathway from biochem, and you have to answer what kind of a reaction it was. We looked at that real briefly when we looked at tyrosine's conversion into epinephrine. Know the reaction types. Number 2 is a lab experiment. So just a straight out, similar to what you did in school or what they do in a lab, where you isolate something, you purify it, you identify it, they give you the data. And undoubtedly, you're going to have to identify a side product. You're going to have to figure out what type of reaction occurred. And then the third one is, I don't know, it's hard to describe, somewhere between a mechanism or a partial mechanism and predict the product. So they'll show a pathway in a question, and then it'll just have R groups on it. And then they'll ask you, what is the compound that was formed, or why was this step the way it was, or what happens if we put this reagent in instead of the reagent listed in the passage. And so in your travels through OChem, how many would agree very memorization heavy? You got a ton of reactions to memorize, like an entire textbook's worth. For the MCAT, you have less to memorize. You have to understand mechanisms more. You have to understand why things happen, but there is some memorization. So on the student guideline, which I'm hopeful all of you look at, the official list of topics that are tested, it'll say name reactions. And name reactions ends up being kind of a mixed bag. So when you think of name reactions, OChem, how many start thinking aldol, Clays, and Grignard? You start rattling off these people's names because for whatever reason we name things after people. Ends up most of the reactions that are meant to be known by name or tested by name are decarboxylation, hydrogenation, dehydration, elimination, the more general reactions. And so fully expect, like, I don't know if anybody, again, tracks Reddit or Student Doctor Network after MCAT test dates, but you sometimes see like people post, and there was a crazy, basically it deals all their spinoff electrocyclic reaction, which if you look at it, it's still fair game because electrocyclic is fair game, but a few people were upset that it wasn't supposed to be tested. And they asked something called the Baldwin rules. And I'll be honest, I went to grad school in chem and I don't remember hearing the Baldwin rules, looked it up and like, oh, it's just the ever so common 4 electrons will find 2. And so it was something like this. So how many vaguely remember something like this, where electrons move around and you end up with a new ring system? And so the question I have for you, yeah, you see it, you recognize it. Would you panic if you didn't recognize the name? Yeah, I mean, that is basically what happens to all of us. You go through this, oh crap, I don't know it because I don't know that name. No, aldol is the one with the carbonyl where you deprotonate at the alpha carbon and then that attacks another carbonyl. Yeah, and the thing is, this is called a Diels-Alder. This is the Diels-Alder reaction. And the Baldwin rules simply say you want a Huckel number of electrons. So basically for this to occur, you want 6 electrons, you want 10 electrons. You have to have a system, and it can come from anywhere. It could be a lone pair and 2 pi bonds, 3 pi bonds, it all works. But the whole point of it is they throw stuff like that seems overwhelming, but the questions themselves hopefully aren't bad. You have to basically overcome that initial shock value of not recognizing a name. So, and for whatever reason, we feel more comfortable when we know the name, but do not lose sleep. Do not waste time trying to memorize a bunch of names. When you see them, think about it for a moment, move on. You have to know generic things. You have to know what esterification is. You have to know what acidification is. You have to know what those generic reactions are, but they'll have different name reactions. So the MCAT's going to have more stress and than it needs to, but it's going to be basic thoughts for the most part. And that's what I'm going to try to get at today then. So my goal for this lecture is to, as much as possible, look at the things they typically like to throw. So I want to start with that molecule right there. It's not necessarily organic, but is that in our atmosphere? So how many learned at some point that we have about 3/4 nitrogen, 1/4 oxygen, and some other gases mixed in? And so it ends up, if you look at the molecular orbital diagram, look at the overlap of the orbitals, it ends up, that's not a good representation. This is a more accurate representation. So what do you know about single electrons? Are those stable or unstable from your travels? Unstable. So this is called a biradical, bi because it's two. But if something is a biradical, then is it going to react with everything? So is O2 so reactive that we actually have an entire class of reactions called oxidation? By all means. Okay, so here's the good and bad news. When we oxidize something, can we get energy? Is this the whole concept of eat food, oxidize it, get the energy? Perfect. But does oxygen know to only oxidize energy molecules in our body, or in theory, can it oxidize everything? So the fact that we're surrounded by oxygen, are we constantly being oxidized? Is that, in essence, part of the aging process? It oxidizes everything. So how come we don't oxidize away very quickly, just like energy molecules? Because technically we are an energy molecule. Well, energy molecule collection. Is our body built with some mechanism to combat oxidation? Antioxidants, exactly. So antioxidants are an entire class of compounds that, for whatever reason, are kind of a passing thought in a biochem class, an OChem class, but was kind of a major thought on the MCAT. I want you to recognize a couple things. I want you to look at this and, as an OChem, say benzene ring, sp2, lots of conjugation, aromatic ring, phenol, because of OH on here. So that's great. But I also want you to note, is this free radical a little more stable or less stable than most? So if I turn that into a free radical somehow, is that going to be more stable or less stable? Why more? Absolutely right. What makes that more stable? Resonance, the correct answer to everything. So because this electron can resonate over here and around the ring, it makes it more stable. So this is what we call in OChem a free radical scavenger, but in biochem, we call it an antioxidant, meaning if O2 comes and oxidizes a molecule in our body and turns into a free radical, can this come and reverse course? Can this donate its free radical electron and stabilize whatever became the radical? So for whatever reason, this is a really important combination of molecules on the MCAT. So this, you can refer to as an antioxidant. I'm going to make it it's one word, but I'm going to make it 2 word, just because for spacing. It's an antioxidant. And what happens to the antioxidant? It's getting oxidized or reduced. Antioxidants, how do you recognize it as being oxidized? What's a good giveaway? Something I can recognize all the time? It lost H's, non-acidic ones. It lost it actually as an H neutral or H minus. So it lost H's, perfect. And it gained bonds to O, perfect. Absolutely right. Everything it did. It went from 2 bonds to O to now 1, 2, 3, 4 bonds to O and lost these 2 H's. So it's oxidation. Antioxidants are oxidizing reagents or reducing agents? That is essentially a verbatim question. It's been asked on a few occasions. Antioxidants are reducing agents because they themselves get oxidized. The wording is always a little awkward, but reducing agents get oxidized, oxidizing agents get reduced. You cause something by carrying out the opposite reaction. So antioxidants are also known as reducing agents. So hopefully that seems okay. Also, reducing agents are rich in H. Okay, so hopefully, does this molecule seem familiar? I actually want to start this as my opening molecule and then go into a little detail of what the goal is of OChem. Knowing the hybridization, knowing the aromaticity, those basics, important, but also recognizing specific functional groups and how they're useful in bio. So anytime you see a phenol, benzene ring with an OH, you should think that is an antioxidant molecule. So in your travels, did that pop up, that antioxidants are phenols? Did that pop up in either biochem, maybe just a general bio class, OChem? Yeah, see, I never learned it, it sort of fell through the cracks, but every class expects you to know that. They just expect somebody else to have taught it. I think that's probably why this is MCAT heavy, because it's a simple thought, has bio applications, and it fuses, brings together OChem, biochem, and I guess maybe cell. I don't know what other area, but in bio. Okay, let me go ahead and toss this molecule up. I'm going to erase everything. So going in 3, 2, 1, clear. So this would be a typical example of some molecule they might give in a passage. Okay. Find in green tea. What color is green tea? Kind of a silly question, but I do mean that. Okay, it's got a color associated with it. Okay, consequently, does that mean it's got pi bonds with lots of conjugation? I mean, that's another random fact you're supposed to know. So what causes color in OChem? In organic molecules, lots and lots of conjugation. So if you have lots of conjugation, then the transition from the pi, the filled electrons in the pi orbitals, it goes up to a pi star or an antibonding orbital, then it can absorb in the visible range. Just want to make note, let's just say it is green. And it's kind of a note of interest because you pointed out green tea is not necessarily green. But let's say it looks green. If it appears green, what did it absorb? I don't know why they love this so much, but they love this. If it appears green, what color did it absorb? So one answer in. The artistic color wheel, the paint mixing color wheel. If you've never seen this before. Roy G. Biv in a circle where there is no I. So it's not perfect. I've drawn my wedges of equal size, but it shouldn't be. But basically, the primary colors, red and yellow make orange, yellow and blue make green, blue and red make violet as I go around. This is approximate. This is not perfect. This is approximate, but around every 50 are the colors. So if you absorb red, what colors appear? And I want to be careful. That's what they told you in GChem to make you believe all colors except green. But then they gave you this graph. So how many of you have ever seen this graph of absorbance as a function of wavelength? So does it look like this, where it's all colors except green? Or is it this? So which graph is correct? That absorbs all colors but green, or that absorbs red and therefore there's no red to cancel green? So left one or right one? From your experience in either OChem lab, GChem lab, biochem lab, when you look at absorption spectra, how many agree they look like this? Nothing, 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 then one major absorption, maybe a second one every now and then. Yeah, it's the right one. So it ends up, this was a lie that GChem professors told you to make your question go away. Really what happens is this opposite, where you absorb light of one wavelength predominantly, and therefore it's not there to cancel. All colors make white. If we take away red, it will appear green. You have to know how to work the color wheel. How many had a GChem professor introduce it early on, the color wheel? How to predict what color something is? Okay, so yes and no. So it's interesting because, yeah. Oh, so, okay, usually it's about 50-50. Oh, I can't necessarily repeat why it is, like for the reasons behind it. That's just the way life works. Materials have one absorbance, maybe a secondary absorbance. They don't absorb everything but one thing. They actually absorb one color. So this is just something you should have seen in biochem, you should have seen in GChem, just spectra like this, where you have a primary absorbance. If we don't buy into that, do you remember any professor ever using the term lambda max? So let's say lambda max said was 689 nanometers. The term lambda max refers to the color of primary absorbance, the one you most absorb. And the color it appears, reflected color. So white light hits it, red is absorbed, green isn't. So violet still cancels yellow, blue still cancels orange, but green doesn't have any red to cancel it, so it appears green. So the question is, why does conjugation equal color? I, you're going to hate me for saying this, but it just does. I'll go into it really briefly, but typically, so I'm going to need to erase to make room. Yes. Okay. Oh, so yeah, Jonathan, thank you for that. 50 is a guess. So it's like the real line might be around like 620 here, and it might be like 590 or something. So these aren't perfect, but they're so close. They're really, really good. And then all colors cancel each other out. So violet cancels yellow, blue cancels blue, red cancels green. When you mix them together, you get white light. How many learn that? All colors equal white. You shine 6 colors on a wall, you'll get a white spot. How many learn that? In the absence of color, you get black. Yeah, so if we have white light shining on something and you take away the red, violet still is there to cancel yellow, blue is still there to cancel orange, but green doesn't have a cancel partner, so it reflects green. Yep, all of them reflect out, they hit your eye simultaneously, and we process it as white light. For us, all colors, when our cones are all stimulated, we see it as white. Okay, so why does conjugation cause color? I'm going to do this really, really fast, but it's going to require erasing everything. So if you screenshot it, screenshot in 3, 2, 1, clear. So it's actually in the spectroscopy handout, if you want to look at it later, but if you have a pi bond, so I'm going to draw just a simple pi bond, your energy levels will be pi and pi stars are called. You get 2 electrons in a pi bond. So energy, when it goes from pi to pi star, causes color. Every single time you add a double bond, you now have sharing across the whole thing, some sharing, some anti-sharing, and complete anti-bonding. And so it ends up the energy levels do this. 1, 2, 3, 4 electrons, because I have 4 pi electrons now. This only had 2. Notice this gap just got smaller. So this is a big gap. This is a smaller gap. Every time you add more conjugation, it keeps on getting smaller and smaller and smaller. And so this gap gets smaller. That's the best explanation I can do in a minute or less of why conjugation equals different color. But it's because as you keep on adding conjugation, the difference between the so-called HOMO, highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital, gets smaller and smaller and smaller. So it might start at like 180 nanometers, turn into 245, maybe 290, et cetera, until eventually once it crosses 400. So good question. So do we need to know this antibonding stuff? Yes and no. So let me tell you a little bit about you need to know about antibonding. What is bonding? Is bonding the sharing or not sharing of electrons? It's the sharing, exactly. What you need to know then is antibonding, would it be sharing or anti-sharing? So just look at that, anti-sharing. So perfect example, let's say there's a freeway or some road. You have two sides of the road. So you have lane 1, lane 2, lane 3, lane 4. Can traffic share those lanes? So in other words, could this car make a lane change there? Could that car make a lane change there? They're going in the same direction. They can share. Electron can go either way. Car can go either way. Same thing here. Can they go either way? Can this car here make a lane change there and vice versa? But what happens when you cross that center line? Is it easy for this one to share into that lane? Yes or no? Shading and spin, exactly. So I'm doing direction of traffic, but how many would agree if I were to just do this in terms of shading, I might do something like this? Meaning, can you make a lane change there? Can you easily make a lane change there? And over here, I could make orbitals like this, representing this lane. So lane changes, because they're going the same direction, no problem. Lane changes go in the same direction. But can you make a lane change across here and here? You cannot. So this would be called bonding. This would be called antibonding. And this would be called bonding. And so that just represents how these orbitals can be. It's kind of overkill. I want to stop right there, other than to simply say shading, we call it plus and minus 1/2, but really what does shading tell me? Shading tells me what direction it's going in. So spinning clockwise, counterclockwise, clockwise, counterclockwise. So can you share when you have different shading? Can you share when you're going in opposite directions? That's a take-home message. Visually, can electron be shared from this orbital to that orbital? No, they're going in opposite directions. You can only share when you're going the same direction. And so I'm going to simply say bonding is always more stable than antibonding. Energy transfer from, or electron going from bonding to antibonding absorbs energy. Antibonding back down releases energy. Let's leave it at that picture. And just know the one take-home message on this one, and it has popped up in MCAT before. What causes color in organic species? Pi to pi star transition. Write that down. If you've never heard that before, it makes no sense. Write it down as a flashcard message to yourself and work your way through it over time. Okay, so hopefully all is well. So I'm going to get rid of this. I'm going to ask you an OChem question now. So erasing everything in 3, 2, 1. This is what like they do. They like to throw an organic molecule, tell you about the bio and the OChem of it, and ask you a mixed set of questions, including some straightforward. Oh yeah, so pi and pi star. Pi represents the bonding orbital. Pi star represents the higher energy antibond. And OChem color is always associated with light coming in and exciting an electron from pi to pi star. Transition. Hopefully, I apologize because I learned something kind of cool from a more experienced online teacher than myself, that this is not the best program for thick pencil tips. Thank you, Sophie. Thank you. Seriously, you have no idea how much that helps. So, I mean, everybody be jealous. Hopefully you can see that's an S in the middle, but that was a star move. So thank you, because a lot of times that just makes my life so much easier. So appreciate you tossing it in there. Okay, so for this one, how many sp2 hybridized carbons are there in catechin? So how would I start this question first off? So even if you don't know the right answer, what are sp2 hybridized carbons? So picking up an orbital that Coy did the other day. So perfect. sp3, it's making 4 bonds. It uses s, p, p, and p. But if it's sp2, then would you agree it's making 3 sigma bonds, sp2, and has 1 leftover p orbital? The p orbital makes that pi bond. So is it sp2 whenever we have a pi bond? And I want you to catch me on something because I'm almost right with what I just said. So is it a pi bond or specifically a double bond that I should be looking at when I start talking about? So pi bonds, you can have actually a triple bond that has 2 pi bonds. So specifically double bonds. So let's go ahead and mark through this. How many sp3 hybridized carbons? So how many agree that's a pi bond, that's a pi bond, that's a pi bond, not a carbon? What about this one here? sp3, sp3, sp3. Okay, so how many agree the ones that form the aromatic ring have to all be sp2? These have to be all sp2. So 2, 4, 6 for this one, 8, 10, 12. So 12 sp2s, 3 sp3s. How many would buy in that? That's not necessarily a hard question, but is it still one that can separate the curve? It's not an unreasonable thing for them to ask. And you need to know your basics. Okay, so fair game. Hopefully it seems reasonable. Would this be an antioxidant? Yep, antioxidant because OH is on a benzene ring. Would this be a colored species? Probably, because a lot of conjugation with an O that can donate in, O can donate in, O can donate in. These lone pairs can share in here. So this one is highly likely that it's going to be colored. Okay. So moving to one more example. Yeah, so how are double bonds sp2? So if I consider a carbon, if it's sp3, everything is making a sigma bond. But if it only has 3 sigma bonds, and then the other bond, oops, sorry, I meant to do that in different color. Then it's making like some bond to something else with a pi bond. So a pi bond has to use a p orbital. So because that's a p orbital, the other ones end up being sp2 for everything else. If that sounds familiar. Yep, so the two things. Yeah, that's the only really common OChem marker. So I think, honestly, this is just straight memorization. If you have OHs on a benzene ring, particularly 2 or more, antioxidant. Because if you lose 1H here, 1H here, you can lose 2 electrons, stay paired, and end up with a nice stable molecule. You got to recognize this as a, I mean, and just out of curiosity, how many have learned this as a really common antioxidant structure? I mean, in bio, how many have learned that this is going to this? And if you have nitrogens doing it, I think those compounds are called flavins. Quinone. These are your quinone. So hydroxyquinone and quinone. Perfect. Yes, and what Melody just said, perfect. So OH on a benzene ring, typically that's what you're looking for. And these are your quinones. Nitrogens are called flavins. Hopefully it seems okay. And then number 2, conjugation. If you have lots of conjugation, you can have this. You have color when you have conjugation because of that transition. OH is on a benzene ring, antioxidant. And again, I don't know why these are 2 really important facts that they like to test, but these show up with reasonably high, I guess, proficiency. I mean, or high frequency. So definitely one of those things you should hang on to, should know. Okay, moving onward then. 3, 2, 1, if you're screenshotting. Is that an antioxidant? How do you know? I mean, how can you say that so quickly? I mean, I have my doubts. The OH, perfect. OH on a ring here. So perfect. This is an antioxidant. Is it a colored species? Even though I guess this kind of gave it away. Yeah, so good question. Would tyrosine be considered an antioxidant? Initially, no, because of the amine group. But once you get rid of the amine group, yes. So in its natural state, yeah, I guess to some extent it is, but it can be turned into a better one. But yeah, that's actually a great question. Okay, so question, was either the O bonds sp3? Because of resonance, this is what's sort of tricky. In order for this to donate in, it's got to take on some sp2 character to form that pi bond, but it's also sp3 as it is. So usually we consider it to have its lowest possible hybridization. So this can take on sp2 alignment. So I typically call this an sp2 or a planar oxygen. Same thing here, this can donate in. And because it has 2 O's, even though a CH3 does come off easily, definitely an antioxidant. Lots of conjugation. So OChem question for you. Yep, so the private message was, so OH on benzene are good antioxidants because they can get rid of an H and the OH can go to donate electrons. Exactly. It can donate electrons via the H free radical to reduce something else. So first off, what's a unit of saturation? I can't remember. Fairly important, I think. You might have learned degrees of saturation, hydrogen deficiency, or units of saturation, different ways of saying. Rings or pi bonds, exactly. So let me briefly address where it comes from. If I have C4H10, would you agree there's 1, 2, 3 H's, 4, 5, 6, 7, 8, 9, 10 H's. So when it's fully saturated, when all the H's that are possible on it are on there. But what if I make it C10H8? Now I have 2 less than the maximum. So I'm going to get rid of 1 H there, 1 H there. And I could have a double bond. An H and an H. So that would be a case of 1, 2, 3 H's, 4, 5, 6, 7, 8, C4H8. If I added 2 pi bonds, I'd have to get rid of 2 more H's. So how many learn this as either hydrogen deficiency, the shortage of H from a fully maximized saturated compound, or how many learned it as either units or degrees of saturation? Do any of those terms, any of those 3, hydrogen deficiency, units of saturation, degrees of saturation, do any of those sound familiar? And every textbook will describe it differently. Degrees of sat, perfect. Okay, that I think is the more common way. That's a term I learned, but some teachers will teach hydrogen deficiency. Some will say units of saturation. Doesn't matter, whatever it is. So I saw people put 5 and 6 in the chat box. So let's go ahead and work our way through and see what it is. So 1, 2, 3 for the benzene ring, 4 for that pi bond, 5, or 3 for the pi bonds and benzene ring here in this. So 5, who said 6? And explain to me why we are all wrong when we stopped at 5. So for anybody who said 6, what are you seeing that the rest of us missed? It's not written out for me. That dang carbonyl. Is there a double bond to O that's really easy to miss? Oh, and be honest, are you thinking a stronger word? It's early in your study, so I get it. That's an appropriate word. But yeah, by the end of studying, you'll definitely be thinking a stronger word. But perfect. And that's, you know what? Lesson learned. Dang it. I should have caught that one. I didn't. Life goes on. I made a mistake now. I'll pay attention to that in the future. And that's a thing that hopefully most of you are starting to realize that, hey, we're going to make mistakes along the way. I learned from them all. And I want all of you to just take this to heart. Whatever you get right or wrong now, does it really make a difference? All that matters is, would you get the question right if you saw it or something like it down the road? And yeah, exactly. It's a growth mindset. We are in preseason. So the reality is, you're going to have to know this stuff for down the road. So no worries. I'm feeling pretty good about this. Okay. So I'm going to go in the opposite direction. I want to see if you can get the formula really fast, and then we can do it. Yeah. And I mean, how many agree that when you get a question wrong, you think about it, you evaluate what you did, you evaluate the information you needed or the way you need to look at it differently? And how many actually do learn more from getting a question wrong and reviewing it, certainly in midterms and finals, than anywhere else? And every time you see a final or midterm, there's a question like, dang, I knew that. How did I get that wrong? You knew it, but you didn't know how to apply it. Oh yeah, practice finals are a gift from the gods. When you have a teacher that gives you a realistic practice final, you should give them a hug afterwards. Except with COVID, you shouldn't. But they're the greatest gift a teacher can give you during school. That's a teacher's way of saying they love you. Okay. I'll do you a favor. I'm gonna help out and come up with a formula. I'll do all the vowels, you get all the consonants. So 1-0, I'm done. So now your turn. How many C's and H's? So I like the C28. Let me just double check. 6 plus 4 new ones, 4 new ones, and 3 new ones. So is this ring structure fairly common? The 6, 6 up here is 5 and a 6. Yep. Known as an androstenedione ring structure in OChem, a steroid ring structure in bio. So let me just take a pit stop. If it has a biorelevance, the chance of showing in the cap a little higher or a little bit lower? Much higher. So important thing, tell me what steroids do for us besides make us better baseball players and run faster and jump higher. Okay, so one precursor is a lot. So for instance, cholesterol is a precursor to pretty much every hormone. So they're lipid-like. You can break them down, anabolism, metabolism, break them down, build them up, definitely. But what do they actually do for our body? Do they do anything? They maybe don't reduce them themselves, but they lead to signaling for something to be reduced. Membrane fluidity, definitely one. Is that true? That cholesterol can incorporate in, and therefore they can impact inflammation and interaction of cells by all means. That's a definite that cholesterol does. But do they also trigger for biological behavior? In fact, you have to, from endo, learn about the female and male hormone cycles. I mean, by all means, do they cause different events? Do they trigger a message for your body to do something? So basically, are they messenger molecules formed in a gland, released in the bloodstream, they target somewhere? So does one hormone go into one cell and that's it? Or does it go into a cell, send a message, then leave? Go into another cell, leave? So something that's really cool, and I want to emphasize this chiral center right here, if I were to draw this ring structure, and forgive me that I'm drawing the chair conformation because chair can't with that pi bond, but if I do something like this, let me draw my chair a little bit better. Let me draw it like this. It's this ring right here. If I have that CH3 up, and that group's down, and so it's going to form something like this. With whatever this R group is. Just out of curiosity, would it seem reasonable this fit in the cell membrane right like that? So how many would believe this to be possible? That this molecule right here, this could slide into the cell membrane because it's hydrophilic or hydrophobic? Hydrophobic. So is it reasonable? Is this kind of crazy, but could this thing actually slide in to the cell membrane because it's hydrophobic could this part right here with its tiny, tiny bit of water lovingness, and because of this chiral center the way it is, can this part, because it's now pointing down, go in the cell membrane, or is it sort of reach a little anchor? Does it buttress in, so to speak? Does it bump against this and cannot go in? This anchor stops it from going in. So can this hormone, this molecule right here, stop at the cell wall or cell membrane here, go across the cell membrane, and then have this part go into the cell and send a message? Can the specific functional groups of chirality over here send a message? Then can it leave, go through the bloodstream, find another cell, go in, send the same message? Was that a pretty ingenious design because of that chiral center right there? I bring this up because of two things. Number one, in bio, nobody ever taught me that that chiral center was a meaning of life chiral center, but it is. And number two, is this right up the MCAT's alley? Take something you know and present it in a slightly different way and then ask you questions about it. So that chiral center right there is a key one because of it sticking straight up, and that makes the ring stick straight down, and so it can't go in very easily. So out of curiosity, again, I ask, how many learned this more of an OChem or physical biochem perspective where the molecule goes in, sends a message, leaves, goes in, sends a message, can go in, go out? Yeah, the whole thing. Yeah, it isn't that the OH holds it in water. It's not that part. It's that if this CH3 is sticking straight up, then that has to be going down, and this one going down. So it's this fourth ring right here that instead of, because could I have also drawn it like this? So could that have also been? So let's say it looked like the purple one. Could that just keep on sliding in further? Would it be harder to leave? But by having this chiral center right here the way it is, pointing down, it forces the ring to go in a certain way. So it ends up the ring points down. Like a hook, like a wall, like an L, if you will. Yes, everybody see what Stephanie said? If this is axial, this must be equatorial, which forces the ring to go in a certain way. Yep, and it's terminology, it really is, but that chiral center in this orientation of that ring is kind of cool. Okay, again, why am I spending so much time on bio in the middle of OChem? Step back for a second, like, what is the purpose? We spent an awful lot of time on bio so far today. Why? Because OChem on the MCAT isn't OChem. OChem is organic molecules that do cool bio things. So for anybody who's taking the MCAT, did any of you see at least one, if not multiple passages of OChem molecules with bio applications? Was that just tons of the test? Not tons of it, but most of the OChem? It's how you have to apply it. It's cool. I don't know about you, but I think this is the coolest example of why stereochemistry matters in this world, if you ask me. Enzymes being D or L, working and not working is pretty cool. Sugars being the different chirality and not binding the site so you can't break them down, pretty cool. I mean, it's pretty neat how chirality that I remember in OChem having to identify R and S. Who cares? I just did it. But when you start thinking about it in terms of bio, it's life-changing. It's kind of cool. Okay, gotten a little too philosophical. Okay, so back to this. So I'm going to erase everything. Sorry, it's going to take a while, but I want to leave the purple up there. So somebody counted it out and came up with 28 carbons. Is that right? 28. So I'm going to say this is 58 O's. So I'm going to tell you that's what we have so far. Perfect. So I'm going to tell you it's 58. Tell me where I get 58 and if I'm right or wrong. So where did 58 come from? What I did is I took 2 times 28, that's 56, plus 2. So 2n plus 2 is the number of H's. So the number of carbons times 2 plus 2, 58. Is it right or wrong? Is 58 correct or incorrect? It's wrong. Why? Ah, that would be if it's unsaturated. And you're telling me there's some rings and pi bonds? How many rings and pi bonds do you have here? Ah, perfect. So I have 6. So therefore, get rid of 12 H's. So how many are okay with that? H's are there. I hope that seems reasonable to you. I don't want to count H's. I just hope you trust on this. But working this backwards. So realistically, tell me, when you took OChem, did professors say, here's a molecule, what's the formula? Or is it usually the other way around? Here's a formula, deduce what the molecule is. Which was the more common question that you got? Second one. Okay, so I need to somehow turn this into some sort of equation that I can use in the future. And so, weird question for you, but how many, if you wanted to make a long chain, so bear with me on this one, but I want to connect things. I want to connect these 3 circles together. Do you agree you need to make 2 bonds to keep it going? So let's say I want to keep a long chain of circles going. I'm going to tell you each of these makes 2 bonds, one on this side, one on that side, 2 bonds, one on this side, one on that side, 2 bonds, 2 bonds. And then the ones on the end, you agree, only make 1. Okay, so I'm going to tell you, to keep a chain going, does everything have to make 2 bonds? If we want to make a giant chain for us, if we want to link our arms and make a giant human chain, would most of you agree we would have to connect with 2 hands on each side? Makes sense. So here's what happens. We start keeping track of what each atom does. So how many bonds does carbon make? 4. Is that the exact number we need, or is that actually 2 extra, we need to keep the chain going? 2 extra. For every carbon, there's 2 bonds beyond the bare minimum of what we need. What about nitrogen? Nitrogen makes 3 bonds. So for every nitrogen, that's 1 extra. For every oxygen, that's exactly what we need. For every hydrogen, we're short 1. So I'm just going to be a bookkeeper. I'm going to say for every carbon, 2. So I'm going to come up with this formula. The formula is going to be the following. 2 times the number of carbons plus the number of nitrogens. I'm going to completely ignore my hydrogens, or my oxygens, excuse me, minus number of hydrogens. And how many ends of the chain? How many things are dangling off the end? You have a left end and a right end. There are always 2 hands at the end of the chain that don't get used. How many electrons per bond? How many hands per linkage? 2. This is the units of unsat, or degrees of unsaturation. For every carbon, you have 2 extra bonds. Every nitrogen, 1 extra. Every hydrogen, you're short 1. I put the negative in there too many times. 2 for the end of the chain, and 2. So let me just apply it real quick, and you tell me how many units of unsaturation. C6H10O2. How many units of unsaturation? Two. Perfect. For every carbon, there's 2 extra electrons, so 12 minus 10. So 12 minus 10 is 2. Ignore the O's. Plus 2 for the end of the chain, 4. Divided by 2. 2 units. What about C10H16N2? 4. Perfect. 2 extra for carbon, so 20 minus 16 is 4, plus 2 more is 6, plus 2 for the end of the chain, 8 divided by 2, 4 units. So how many find using equations challenging or remembering the equation is challenging? Which one is more challenging for you? Using it or recalling it? 1 vote for remembering. I'm going to toss my vote. Remembering, recalling it by all means. So focus your energy on where you're going to need it. If you know you're going to be able to use the equation, then I'm not even going to have a second thought. I can plug in, I'm good. I have to remember this. This is really hard, but if I think about it in chain, if I can figure out what atoms do. So for instance, what would you do with a halogen? Let's say there's a chlorine in the compound. How many bonds do chlorines make? 1. So what would you do with chlorine? Would you treat it like a carbon, nitrogen, oxygen, or hydrogen? Treat it just like an H. What if phosphorus was in there? Phosphorus makes 3 bonds. What would you do with it? Treat it like an N. Perfect. So if you know what they do, 4 bonds, 3 bonds, 2 bonds, or 1 bond, can you figure out what to do in the formula as needed for it? Definitely. Okay, I'm going to throw a question at you. It's a hidden question, so do what you can with it. So if you want to screenshot it, now's your time. I'm going to switch over in 3. Oh, where do we include oxygen? You don't. So why is oxygen? So somebody explain to me why oxygen is not being included in the equation. Why am I so anti-oxygen? That was a pun. I'm anti-ox. It only forms 2 bonds. And how many do we need minimum to keep the chain going? 2. This is a summation of the extra bonding electrons. Oxygen provides no extra or no shortage. So we just ignore it. We ignore the oxygen row. So, oh, you're welcome. It's pretty easy to determine it. I think it's actually easier to deduce it if you know how many bonds things make in 2 minimum. Just this +2 is the one that's tricky, and then 2 electrons per bond in the denominator. So I'm going to turn you loose. I'm clicking in 3, 2, 1, and you're off. Okay, for this one, oh my gosh, I have no idea how to start this one. So I'm going to tell you what I think is true, and then I want you to evaluate how useful what I said was. I see the word aromatic, and I think, oh, Huckel's rule. I remember this, Huckel. And I remember 4n plus 2 pi electrons. And, oh, cyclic. I remember cyclic was important and conjugated. So I'm feeling really good, and then I don't know what to do. Okay. Useful or not so useful approach so far. Terrible approach. Okay. How many, instead, when you see aromatic, think benzene? I mean, be honest. How many think when I say aromatic, benzene ring? Yeah, it's pretty much what we're going to do. So therefore, when we think of how to answer questions, should you try to come up with definitions and ways that are unnatural, or should you always build an answer from your natural instinctive reflex? And this is the problem with answer explanations in general. They're written by somebody who thinks possibly different than the way we do, and there are a bunch of definitions. You have to modify it. So for me, first thing I'm thinking, aromatic equals benzene. How many units of unsaturation in benzene? 4. 3 pi bonds in a ring, perfect. So I'm looking for something with 4 units of unsaturation. Okay, fair enough. So only one answer can be right. Which one is most likely to have as much as 4? Something with very few carbons or lots of carbons, lots of H's or very few H's? Which is probably the one you're leaning towards? Okay, so let's go with D. Let's start with this one. What do I do for carbon? The formula? Times 2, exactly. So 2 times 8, 16. What do I do for hydrogen? Minus 1 each. So 16 minus 11 is 5. What do I do for N? Plus 1, 6, plus 2 for the N chain, 8, divided by 2. 4 units in saturation. So here, minus or plus 16 for the carbons, minus 11 for the H's, plus 1 for the nitrogen, plus 2 for the end of the chain, divided by 2 is 4 units. Could that be a benzene ring? Is it possible that maybe this is our compound? I'm going to draw one out, and I don't know if that is our exact compound, but let's see if this works. 1N, 6, 7, 8 carbons, and 6, 7, 8, 9, 10, 11. Perfect. Works beautifully. If there's 2 more H's, 1 less unit in saturation, 1 less carbon, 1 less unit in saturation, and so forth. So I'm going to agree the best answer. The MCAT is built to punish people who overthink. And let me just emphasize that. I'm an overthinker. I know this, and I say, wait a minute. Hey, test writers, what about this compound? Would that be aromatic? Let me draw that a little bit better. Is that an aromatic ring as well? Benzene ring is 4 units. 4 units because 3 pi bonds and a ring. So count them individually. But this one's aromatic because it has a pi bond, and a lone pair. They can all resonate. So it's cyclic, conjugated, and then I have 2, 4, 6 pi electrons, which meets that rule. So yeah, that could be aromatic. So in theory, C could also be right. How is the question worded? Which is definitely aromatic, which is usually aromatic, which is always aromatic? Likely. Is there some ambiguity? So which means this is looking for a perfect, always right answer, or the best answer most of the time. Best answer most of the time. This was one of the hardest things for me to wrap my head around, is that there can be more than one right answer, but there is only one best answer. Once you get used to it, once you see it and work your way through it, it's fine, but it's kind of unnerving at first. Okay, so was this a hidden unit of unsaturation question? I mean, totally doable. It's applying information. I like it. Feeling pretty good about this. Okay. People seem to do pretty well in this. Okay. One more question. Let's see how you do on this one. Again, give you 40 seconds. Sorry you hear me get up each time. I just like to walk around in between. Sorry. So for the previous one, so where do you get 18? Because how many carbons are there? The previous one for choice D, 16, 2 units for each carbon, so 16 minus 11, plus 1 plus 2. So change your 18 to, so Vinay, on yours, change your 18 to 16 because you only had 8 carbons, and change your 13 to 11 because you only had 11 nitrogens, or hydrogens, excuse me. Okay, so for this one, I love this. How many are kind of pissed off at this question? Honestly, because you should be. I might have made a mistake on this one. So let's see. How many units in saturation in this one, first off? Let's start with that. 2. 14 minus 12 plus 2 divided by 2. 2 units in saturation. Okay. So does that help me at all? Sure. 2, that's looking good. 3, that's out. 1, that's out. 2, we're good. So I'm down to 2 choices. Let's just double check then. 7 carbons, 6 in the ring, 7, 1 O, and then 2, 4, 6, 8, 9, 12. This one works. Let's see. 2 plus 5, 7 carbons, 1 O, 2, 3, 4, 6, 8, 10, 12. Dang it. There's 2 right answers. Did I write a bad question then? Is this a complete or incomplete question? You can go from 4 choices to 2, but you can't go any further. So help me to be a better test writer. What could you do? What could you add to this question? What change could you make so that we can distinguish between A and B? So units in saturation formula can only get me so far, most likely, but then again, I still don't have enough information. Which one's potentially more stable? So can I start looking at comparisons of this compound to this compound? Okay, more stable with what? So for instance, this might be more reactive with the Grignard. This one might be more reactive with hydrogenation. This might be more reactive with NABH4. This is going to be more reactive with H2PD. Okay, that's one way though. Pick a reaction they can do. How else can you distinguish compounds that took up a pretty much a part of your OChem travels? Did anybody ever have a professor that brought up anything with NMR, IR? Oh, yeah. No, it's not your nightmare because it's multiple choice. It just became so much easier. You don't have to come up with one question out of 4 billion in the world, or one compound out of 4 billion. 1 out of 4. So let me change this question ever so slightly. So I'm going to click in 3, 2, 1. Is this the same question? Is it everything we just did, but now we have that part? So let's get to exactly where we used to be. How many agree this random fact is the key feature in this question now? Okay, so 3 ways to answer it. Number 1, there's a person who knows everything in OChem. They remember everything. They memorized what 1714 means. Option number 1, good for you. You know it. Okay. Okay. Who falls in the category? I don't remember squat. That was ages ago, and I didn't like it then. Not liking it now. Okay. The second category, somebody just posted. Let's see, let me go up. Aditya, you are person number 2, category number 2. I noticed you put something with a question mark. So how many fall in the category? I just have a gut feeling because I think IR pretty much just told me about OHs and carbonyls. How many remember that's pretty much all we ever did? Hey, it's a carbonyl. Hey, it's an OH. Hey, it's both. Okay. So first thing, you memorize it completely. Number 2, you trust a gut feeling. And then number 3, you BS your way through it. I'm a firm believer in method number 3 when I have to be. I have 0 pride. I don't care if I get a right answer by the OChem approved way. I'm going to tell you the following. How many signals did they give me? How many numbers of interest did they give me in the question? Just one absorbance. How many interesting functional groups in choice A? How many interesting functional groups in choice D? So in A, would you agree you have a carbonyl and the rest is hydrocarbon that I don't care about? For this, I have an alkene and I have an ether. I have 2 interesting functional groups. Is that, although a stretch, is that still a reasonable way to make a decision between A and D? 1 absorbance, 1 group. 2 absorbances, probably 2 interesting groups. How many are okay with resorting to that sort of BS logic at the very tail end if you have to? So that's what you did? Perfect. If nothing else, it's a last resort, but guess what? I have 0 pride. I want to go to doctor school. If I get a few questions right by this method and it gets me 1 more point in 3 of the 4 sections and I get 3 points higher, and that's the deciding factor of me getting in, not getting in, Oh, hell yeah. I have no pride whatsoever. None. Your job, swallow your pride, make whatever choice has some test-taking logic to it. Go ahead and process your way through it. That said, I should memorize a few of these. Yep, you do not get pretty points. Win by 1, win by 100, doesn't matter. You still is what it is. There is no such thing as a moral victory. There's no such thing as an ugly win. Oh my gosh, do I sound like a horrible coach? So it's just the way it is. So when it comes to moral victories, I'm undefeated. Of course, I lose all the time, but I'm not even going to touch the playing dirty part. It's called playing smart. Cerebral players. Buzzword for dirty players. Okay. So here's what I need to know. Yeah, see that, in all honesty, no, I am a firm believer in hard work, but yeah, I definitely, I would position my way because I couldn't run as fast, wasn't as strong, any of those things, but you can now play it. Perfect question. Everybody see that question that I'm assuming over half of you had? Yes, you got to know some. The AMCAT officially says in their guideline, you must know common eye absorbances. There's only a few, only a couple. Oh, I have no idea what that stands for. FML, I have no idea if that's some profanity or not, but I'm so sorry, I'm an old person. Future of my life, okay. Yep. So, and Tiffany, I know we can't go into detail, but did the question require you memorize numbers precisely between an ester and an aldehyde, for instance, or was it a general close enough number? General, exactly. Okay, that's a message we want to send to everybody. There's a table in the book that's going to stress the heck out of you in spectroscopy. It's going to list all these different carbonyl absorbances. And what I want you to know when you go through the book and you freak out with all this information, it's not there because you have to memorize it. It's there so that you freak out and see a trend. So seeing a trend when they give you a bunch of numbers is important. And then knowing general numbers when you don't need to be as specific. 1700, OH is 3400. Got to know those. It's about double. And notice that you probably learned this as 35 to 36. I'm making it 34 because it's easy to remember double. The other thing is this one is broad. Why is it broad? What does that mean? Oh no, bond association energy, see the trend, but don't memorize anything. I mean, the only few bond lengths and bond orientation angles and bond strength you might want to know all have to do with folding of DNA and folding of a protein, alpha helices, beta pleated sheet. But no, broad because of H bonding, exactly. So OH groups generally get broad. The more H bonding, the broader they get. I'm going to totally pick on that in a second here. The other thing, what the heck does this mean? Plus or minus, plus or minus, plus and minus? What does that mean? It can be a little higher, a little bit lower. So higher or lower. So it might be 1720, 1680, 36, 33, somewhere around there. This means it only be a little bit higher, only a little bit lower. Here's the reason. SP2 is a little shorter or a little longer than SP3. SP2 is a little bit shorter. The more S character, the S shorter. And if it's S shorter, it's S stronger bond. So it begins with S, more S character, means shorter, stronger bond. So because it's stronger, it's harder to break. If it's harder to break, is it also harder to stretch? So alkenes and aldehydes will show a peak above 3,000 for this H. And then alkanes will show it below 3,000. Really, if they go into that, that's a little bit nitpicky, but that's still fair game. But this is your exhaustive table of what we need to know. Okay, My job, you know, I get job satisfaction. I like to mess with you. So what time is it? It's mess with you time. So I'm going to let you tinker with this and we'll talk in a second. Okay, for this one, this is what I got to admit, one of the things I love about the MCAT, and I probably shouldn't use the L word to describe the MCAT, but they do some really cool things, and that is they make you connect different parts of your knowledge. So in 2 totally independent time periods in your OChem travels, how many learned, number 1, hydrogen bonding causes broadness of a peak? A little bit of H bonding, medium amount, lots of H bonding. How many have learned that at some point? Oh, okay. So somebody asked a question. Let me address this real quick. So somebody asked, is that really how much time we would have on exam? I didn't even have time to read the question. No, it's not. On average, so let me just say, if you spend 3.5 minutes to process a passage and 1 minute per question, let's see how much time it would take. 10 passages, 59 questions, so 35 minutes, 59 minutes. If I add those together, 94 minutes. How much time do you have on the MCAT? Sorry for the terrible writing, but how much time do you have on the MCAT? 95 minutes for the science sections. So yeah, it's 95 altogether. So an hour and 35 minutes. So oops, yeah, train for 95. And hence that whole idea of doing 90 to 95-minute blocks of studying. So I should be giving you a minute per question. How much time am I actually giving you? 40 seconds, and I'm giving you harder questions. Remember, this is average time. Hard questions, 1.5 minutes. Easy questions, 30 seconds. Average question, about a minute per question you should be spending. So yeah, I am definitely screwing you over like nobody's business. No, yikes is one thing, but how would you rate this question? Hard, easy, or medium? Easy if you see it. Medium? Okay. Yeah, 10 minutes per passage is you got to get a tiny bit faster than that. 10 minutes per passage would put you 5 minutes over. And so, but for now, perfect, get a little bit faster with time. But yeah, I think this is medium to hard. So this might be something that I should take a minute to 1 minute and 15 seconds for. So I stopped you at 40 seconds. And if you feel totally cheated, well, one, you do get more time. But then also the art of getting ready for the MCAT, and this is the hardest thing to grasp, but it's also learning to get fast as well as get methodical, get things right, but is also get things right fast. Great John Wooden quote, and I love it, but be quick, but not in a hurry. Don't dilly-daddle, systematically go through things, but focus. Don't race, focus. Go quick, not in a hurry. Okay, so I'm going to get rid of this and say for this one, 2 features. The broader the peak, the more H bonding. And did you learn anything about H bonding affecting boiling point? Okay, so while we're on it, why is there 6 chem physics books, 30 topics for 9 passages? Well, it's 10 passages. And why are we disproportionate that way? Because it's pretty much the way people have learned over the years. The amount of material covered, it's a misconception. So I will ask you this, which has the most topics? So are all 4 tests weighted equally score-wise? They look like it. All 4 separate cards are given the same amount of time and questions. But which section covers the greatest volume of material? The number of possible tested topics? chem physics. And reality is those 30 chapters, actually some have a little bit of bio in them. So I would contend the 40 chapters for the bio and chemistry books that we have for 2 sections and only has 7, well, truth of the matter, yeah, psych book is the story for another day. And I hate passing the buck, but I'm just going to say, yeah, that it is underrepresented in what we present, but not by as much as you think. The amount of work that people put in to improve is the easiest in psych soc. I hate to say it. It's rude as a non-psych soc and devalues it, but it's just the reality. There's less to study there, and you can get it fairly quickly. Chem physics and bio, there's just a greater volume material. Yep. But then when you think about it, isn't it kind of unfair that one test that tests so much stuff gives you the same numerical value as another one? But the great equalizer, when you apply to medical school, yeah, they'll see your overall school score, but what score do they give the most consideration to? And I love asking this because if you answer one thing, it means you've been programmed by salespeople. And if you answer another, it means you've actually looked at AAMC data. What section has the highest average for people matriculating to medical school for the last, 31 years since they did it? Oh, the score is a human being, that is true. Casper, not really. Nope. Cars, and I love when people say cars because that's the thing that some salesperson loves to tell you. Cars is the one that predicts your board scores. Actually, it's not true. There was no study done like that. They did one, but it wasn't conclusive. Somebody decided to say that in a meeting and it propagates. Your bio section. Look at the acceptance rate for medical school. Look at all the AAMC release data. What are the numbers for people accepted and matriculated to medical school, their averages? Every year, 32 years in a row, since they've had this style of MCAT passage-based. In fact, yeah, so 32 acceptance pools you should see, bio-sci. Oh, you might need a 125 on cars to get accepted. You need a 125. If you got a 125 on cars and a 130 on bio, or you got a 130 on cars and 125 on bio, you have a much better chance of getting in with the 130 on bio than the 130 on cars with the other one, 125. It's just statistically what it is. And it makes sense. Med school is bio. People are biased, plus they know how intense that test is. So at the end of the day, your overall score, but bio is most important. Cars or chem physics is second most depending on what school you're applying to. Different schools. If it's a research-oriented school, I'll bet they look at CP. If it's a holistic school that wants to do more general medicine, and again, I'm speaking very generally here, but cars or CP will be your second most or third most. And psych soc, a lot of times because it's still the newest test, and some places don't fully know what to do with it and don't necessarily fully trust that it's a viable score yet. And in time they will. And again, what I'm saying is now, if you're applying 10 years down the road, those rules will probably change. But for now, bio is the most important. So just weigh all that in. Getting way ahead of myself, got to get the score before we worry about it. So broadness, hydrogen bonding, but also how many learned hydrogen bonding affects boiling point in some way? I can't remember how. So for terms of boiling point, let's see. For boiling point, I know if molecular weight goes up, boiling point goes up. I know that. Heavier things harder to lift. So is there intermolecular forces? If the forces go up, boiling point goes up. So more H bonding, higher boiling point. So did this question take some bizarre relationship between broadness of a peak, which says more H bonding, and make you make a decision about boiling point, which depends on H bonding? Is this a really bizarre but kind of reasonable concoction of two different concepts put together? So a few things I know. Do they all have the same molecular weight? So how many degrees C is gone? So that's gone. How many would agree the greatest boiling point would be the most polar, not least polar, if polarity was the key? So false and false. And I don't know, for some reason, it's always easier for me to get rid of things that are false than it is to actually make a decision. So the question is, which one, compound 1 or compound 3, is going to have the greater boiling point? Same molecular weight, so that part's the same, but which one has a stronger forces holding together? So we got a 1 vote. So I got another 1 vote. Got an A vote. Ooh, got a B vote. Compound 3. Ah, so somebody, there's the key thing. Broader means, and how many would agree this is broader? Narrow and broader? Broader equals more H bonding. What does more H bonding mean? And that's the thing. Nobody notices because that isn't the way we were ever asked questions before. The MCAT presents things in a unique way. More H bonding, broad absorbance, stronger H bonding, stronger H bond, that one. It is okay. If you got this wrong, that is fine. This is a bizarre, weird question. Yep. So this is totally true. This is higher number. You're absolutely right if it is what it is. Now the question is this the energy of the hydrogen bond or the covalent bond that we're stretching? So this represents the OH hydrogen bond or the OH actual covalent bond, this number. This is the covalent bond. If the covalent bond is strong, the H bond is weak. If the covalent bond is weak, the H bond is strong. So it still fits, it's just kind of, oops, the other way around. Yeah, exactly. The boiling point doesn't depend on the OH bond, it depends on the hydrogen bond. So a strong OH bond means a weak hydrogen bond, which means low boiling point. A low covalent bond means a higher, stronger H bond, which means higher boiling point. Okay. Tough question. This one, same thing. So hopefully this goes a little bit quicker. Okay, try to make it back sooner this time because I'm assuming this one went a little faster. How many got rid of choice A right away? I see no choice A's, so why do you get rid of A? No H, perfect. An ether would have an OR, not an OH, and clearly this is an OH compound, every single one of them. So compound 1, OH, so ether is out. And then how many got rid of choice C next? And explain why you did that. That's test taking. So anybody get rid of choice C? In between, exactly. Compound 1, do you agree, is an extreme compound. It's at the extreme end. So we don't want something in the middle, we want something extreme. Okay, it's not gonna be a perfect answer, it's a best answer. This one, I would guess secondary. This one's primary, tertiary, tertiary, primary, we'll see. So now I need to figure out what does tertiary and primary mean? So it is the narrowest absorbance, least H bonding. And now in terms of what this means, how many learned that tertiary means it has 3 R groups on the OH? Primary means it has 1 R group and 2 H's. Which of these two is more crowded and therefore is it going to be harder for the two molecules to come together and form an H bond? So in which case is it going to be harder for two things to fit closer together? Tertiary is more crowded. Because tertiary is more crowded, its H bond is going to be weaker. So let me just make this note then. So more crowded. Therefore, less H bonding. Less H bond. Hopefully it seems okay. Is this a weird way to look at stuff? I mean, you definitely learned tertiary, primary, you definitely learned broadness of peak meant hydrogen bonding. But is this kind of weird to apply it in this way? Is this taking it in a different direction than OChem did? OChem made you memorize it. OChem made you understand it. But MCAT-wise, are you now forced to apply it in a way that isn't exactly what you're used to? The logic information is all there, but it's just asking you to connect it differently. This is the biggest message I can send lecture-wise is know the stuff, but more importantly, know how to look at it and think about it in an atypical situation, something you're not used to. NMR value, we haven't really done NMR yet. So NMR is magnetic field. The electrons will affect the local magnetic field, spinning electrons. So that's a whole different ball of wax. So primary, secondary, tertiary would be kind of hard. Oh, okay. So in terms of IR, so what happens is the stronger the H bond, the more this H is being pulled away, the weaker the covalent OH bond, and the number goes down and the broadness goes up. So basically what we're saying is I have a bond here, an OH bond, and I'm going to get an absorbance for that OH covalent bond. But because this one has a little bit of H bonding, not very much, it's going to be very narrow and a very high number, stronger bond. But when I have it primary, another molecule would come in and start pull that H away. If you pull the H away, this bond gets weaker, hence a lower number. And because it can have more H bonding, it gets broadened out. So that's basically what we're looking at is how much H bonding affects this. So H bonding weakens a bond and broadens it out. So broader, weaker absorbances, lots of H bonding, narrow, stronger absorbances, less H bonding. That's the take-home message on this one. And that's hopefully when you see that, it's like, I get it. It's applying what you know in a slightly different way. Okay, moving on. What is the most important thing in OChem? In other words, what is the right answer to every question? Resonance. Resonance explains everything. In OChem, how many of you had a professor that said, draw all the resonance structures, the one that has the most wins? I mean, how many would definitely agree you had some professor that made you waste paper by writing lots and lots of structures? Okay, there is some truth to that, but the bigger truth is, do you have time to write multiple resonance structures on the MCAT at a minute per question? Not at all. We have to shift from a mentality of quantity to quality. So I'm going to care far more about what type of resonance it is. So I'm going to tell you there are two things I want to consider. Electron withdrawing groups. There's going to be a pi bond. Electron donating groups. That was so terrible, my writing. So let's see if I can figure out what I mean by this. So let me go ahead and draw a resonance structure. This lone pair, I'm going to say donates in, kicks out that pi bond. Actually, I'm sorry, let me redraw this. Shoot, it's too late now. Okay, what I was going to do, I want to draw it like this. I want to do that, like that. Anything wrong with the green arrows I've done? So anything wrong with my green arrow resonance? I so apologize that I've doubled up everything there, but what have I done wrong for anybody who recognizes it? Triple bond is still a pi bond. That's fine, but the real thing, the X, did I just break a sigma bond? Cannot break sigma bonds. Cannot have a leaving group this. Nuclei don't move, so I can't have a leaving group leave. So everything I did in green is wrong. So I think it's always easiest to recognize the pi bond and build from there. So pi bond, electron withdrawing, so pi bonds pull away. When this pulls away, carbon now has a shortage of electrons, so can these lone pairs donate in? So which is the more stable resonance structure, the one on the left or the one on the right? The one on the left. Okay, let's consider the rules. First and most important, doesn't meet the octet rule. So what is the octet rule? Octet rule. Does everything have 8 electrons except for hydrogens? 2, 4, 6, and the bond makes 8. 2, 4, 6, 8 because of the 4 bonds. 2, 4, 6, 8 because of the bonds. Check. 2, 4, 6, 8 with bonds. 2, 4, 6, 8 with bonds. 2, 4, 6, 8 with bond. They each make the octet rule. So they're both good on this. We're tied. So next rule, what does it mean about charge sites? So let me just ask you something. Which is a stronger base? That last lone pair was terrible. Which is a stronger base, water or OH minus? Second one, how many agree OH minus? Much better because negative charge can be donated and shared more readily. So my question to you then is, if this is more reactive, does that make it more stable or less stable? Less stable. More reactive equals less stable. So is that our rule? Charges equal less stable. Negative is a better nucleophile, plus is a better electrophile. These make them more reactive. Charges are more reactive. So if we want stability, we want less charges. Okay, I got that. So based on that, is one of these better than the other? Which one's better? One on the left. Perfect. And then last but not least, every now and then you have to have charges. Every now and then it's an anion or a cation. You have to deal with a charge. You want to put the charge where it's best suited. Negative should be on O. Positive should be found on nitrogen and or carbon. Positive on less electronegative, negative on more electronegative. Yeah, so, okay, so question confused. The book had examples of donating towards a carbonyl carbon, not the way around? Yes. So exactly, so let's do a carbonyl. Let's say I have some N with some H and an R group like that. Okay, I'm gonna draw a resonance structure. I'm gonna start with the rule, pi bond is the first thing to look at. So the pi bond's gonna break, that's an electron withdrawing group, which means this lone pair is donating towards the carbonyl. Exactly. The lone pair is acting like an electron donating group. The pi bond is acting like an electron withdrawing group. It's always that way. Pi bonds are going to pull away. Lone pairs are going to donate in and become pi bonds. So lone pairs become pi bonds become lone pairs. So not what do they become, but what are they? So let me do the next example. Next page is going to have this specifically. So if I toss that in, this is my baseline. This is this compound. So when I consider the group that is different, I have a carbonyl, I have an H, and I have a lone pair. So the question is, the first thing you need to look at, this pi bond, what's true of a pi bond, withdrawing or donating? Withdrawing. So it's going to go like that. When it does, it's going to start taking electron density. And ultimately, is the group at the other end the one that gets screwed over? So I'm going to get rid of my arrows and put the prettier ones in. So if this is true, this would make this an electron withdrawing group because it's a pi bond, which makes this other end of the molecule up here electron rich or electron poor. Perfect, electron poor, exactly. So electron withdrawing group pulls electron density away, makes electron poor. If it's electron poor, is that more or less like H plus? Is H plus an electron rich or electron poor species? H plus? So this H up here, you agree, is going to be more like H plus. It's going to be electron poor like an H plus, which means it becomes more acidic. It's more like H plus, so more acidic. When things get more acidic, pK goes up or down. If something's more acidic, pK goes down. So it goes from 10 down to 8.8. So tell me what you predict here before we do anything else. First off, lone pair. So lone pair would make this electron donating or withdrawing. What's your gut feeling? electron donating group. Perfect. That's probably going to make this other end more or less electron rich. Perfect. Electron rich, exactly. So if this end is electron rich, it's going to be a better nucleophile, a better base, but a worse acid. So what do you expect to have happen to the pKa? Goes up or down? It's going to go up. At some point, how many of you had a professor that asked, rank those acids, predict that pKa, which acid is stronger? Did anybody have a professor ever ask to decide? So 1 yes, 2 yes, 3 yeses, 4 yeses. Really, really common question. Phenomenally common question. They love to ask you, rank those acids. Tell me what happens in pKa, which acid is stronger, which nucleophile is better, where is it more reactive? They love this. Yeah, so it could go back, but the thing is, you're absolutely right. Can't OH donate in, but is OH on every single one? And so when comparing these, should you compare what's alike or what's different? The thing is, yeah, this OH could donate in, but so could this one, and so could this one. So the reason I'm ignoring that, you're absolutely right. I'm not comparing this OH. I'm not comparing that carbon. I'm not comparing the ring. I'm only comparing that which is different to decide how they compare. So does that make sense? So what you're saying is completely 100% true for all three. So it's not a distinguishing feature necessarily. The distinguishing feature is that group. So hopefully it seems okay. Perfect. So 2 you have to know. You have to know phenols, pK is around 10, and carboxylic acid's around 5. I'm going to just real quickly give what I'm going to call the 5, 10, 15, 20 rule, which is not a good rule at all, but I'm still going to use it. Carboxylic acids are typically 5-ish for pKa. However, carboxyl terminal is like 2 to 3, side chains are 3 to 5. For 10, phenols that we just mentioned, thiols, and amines are typically pK of 10. Alcohols are 15. Alpha protons, let me draw that much better because I'm struggling to see that. So these are going to come in 17 to 20 or so. Alcohols are pretty much exactly 15. Thiols, phenols, and amines are 9 to 10. Side chain of cysteine is actually a little bit lower, around 8 or 9. So these aren't perfect, but how many have seen enough that these are close? So pKs, if you're lost, guess 5, 10, 15, or 20. Carboxylic acids are the most, alphas are the worst. So last one I drew is this compound. Let me draw it up here and not squeeze it in. It's known as an alpha proton. pK equals around 17 to 20. So that's what I mean by that one right there is this one down here. This is called alpha proton. So one that when I deprotonate, there's a resonance structure. So basically the aldol reaction, the Claisen reaction, where you deprotonate an alpha and then it turns into nucleophile. So does that one seem familiar now that I draw it in a prettier, better way? Okay, perfect. I'm going to erase my pink real quick. Actually, what the heck, I'm going to leave it there. So carboxylic acids, my guess is around 5. This one ends up being 5. What if I put a nitrile group on it? Is this electron withdrawing? Oh, it is CH3. You're absolutely right. I could have CH3, but I'm emphasizing the alpha proton. And it could be either of these three or all the acidic one. So exactly, it is a CH3. This group, withdrawing or donating, what's your guess? Withdrawing, which means, what do you predict? Lower pK, perfect, 3.4, okay? Going to mess with you now. So forgive me on this. The inductive effect. Inductive effect ends up being something that has nothing to do with no lone pair, no pi bond, so it cannot be resonance. Okay, good question. Let's go back to this. I'm going to so regret, I just realized I'm going to have to punch everything in again. I'm sorry. Okay, so somebody tell me, how did I know that was a withdrawing group? So what's a dead giveaway for electron withdrawing group as opposed to an electron donating group? What's like that telltale feature I should recognize? Pi bond. Okay, so pi bond typically goes from electron withdrawing group lone pairs. So let me go in the other direction. Let's just say we did want to, shoot, I already changed the page, so I can't erase, so I'm gonna just do it the old fashioned way. White it out. So if a pi bond goes like that, anything wrong with that resonance structure we just created? So let's say I want to assign it to a donating group. Does anybody see anything wrong with me drawing it that way? Broke the octet rule. Exactly. I now have 2, 4, 6 things. That cannot exist, so it's not going to be a donating group. Okay, and it's good to see it 1 or 2 times, but after you've done this mistake a few times and see that you can't do it that way, please go back to the simple rule. Pi bonds break and pull away. Lone pairs donate in and push forward. Lone pairs push in to become a pi bond. Pi bonds break to become a lone pair. How to break the octet rule? Tell me how it obeys the octet rule. What is the octet rule? 8 carbons. Perfect. It has a lone pair, that's 2. It has this bond and this bond, so 2, 4, 6. Where's your 7th and 8th electron on that? So can't do it. Can't have 5 bonds, can't have 3 bonds. Has to have 4, or electron pairs, I should say. Okay. There we go. So that group, when I finally pop it in, oh, there we go, finally popped in. No lone pair, no pi bond, so it can't be resonance. So instead, I just need to consider what it is. Which is more electronegative, carbon or hydrogen? Carbon. How many have seen this mnemonic before? The relative electronegativity for common elements in OChem. F is most, H is least. So anybody get taught by a chem professor or TA of some sort that you should know your good friend Fonkelbrush? Perfect. Good way to remember it. C is more electronegative than carbon, so H is going to give to C, which makes it slightly delta minus, which can share, share, and share. So the thing about the inductive effect, let me go into something called induction in physics. If I have a sphere with 6 pluses on it, can that influence this other sphere to have the negatives go this way and the positives go this way? So in other words, even though they're not touching, can this sphere have an inductive effect, induce charge movement to create a dipole? So can a charge on one induce a dipole on another? So tell me what you know to be true intuitively. If you don't remember this from physics, tell me what your gut instinct tells you. If this gets further away, would the impact be greater or smaller? So if I move this sphere away, would it be a stronger, smaller force? Smaller, okay. And if I move it closer, it would be stronger. Perfect, exactly. Okay. Well, what if I made it +8 instead of +6 and make a bigger charge? Would that have a stronger or weaker impact? Stronger impact, exactly. +8 is going to pull it more tightly. If I only made it +4, less. So are we in agreement then that the inductive effect, induction, proximity, closer you are, the stronger the effect, and bigger the plus, the bigger the charge, the bigger the impact. So same thing holds true. Is this really close or is this far away from that OH? How many agree? That's a judgment call, what is far and close. But generally, if it's 1, 2, 3, 4 or more, it's far away. So it's going to have a large or small impact. Small impact, because it's so far away, it might make it go up ever so slightly. Okay. CF3, what's CF3 going to do? So it's 5.0 without it, but with CF3, it's still far away, but is F a lot more electronegative than carbon? So CF3 should have a bigger or smaller magnitude of impact than CH3. Bigger impact. So it should make the pK go up or down first off, and then by more or less than 0.6. Lower pK, more acidic, pulls electron density away. And should it be 4.4 or even lower? So CH3 may change it by 0.6, should go down, and by more than that, so about 3.8. So inductive effect is not as strong as the resonance effect, but it still is notable. But again, proximity, distance, the further away, the less of the impact, and size of the charge. More electronegative the atom, the greater the inductive effect. Okay, how many agree inductive effect is just used when you have no resonance? It's like, it's not resonant, so I better think of something else. Basically not as common, but not as strong, but it's still there. Okay. Stereochemistry, you got to know your chairs. Got to know your chair conformation. And honestly, not necessarily because of cyclohexane, but do sugars, do aldohexoses assume a chair conformation? So just a little side note. Actually, let me draw it. Let me draw the more common form. Let me draw it like the one on the right. This is typically the way we draw sugar. Everything on this sugar is equatorial or axial as I've drawn it. Everything is equatorial. Would you predict that to be more stable or less stable than axial OHs based on what you've learned in your travels in OChem? More stable. So this is beta D glucopyranose, meaning this is a 6-membered ring, hence the term pyran. It's built from glucose. OHs are all lined up the way they should be. D, meaning this chiral center right here, the last chiral center or next to last carbon has an R stereochemistry. And beta, meaning this group and this group are cis to one another. So I'm not going to go into detail. I'm going to wait till that lecture to go into it, but I just want to at least point out that it's a loaded name. How many learned that beta-D-glucopyranose can turn into cellulose polymer? That cellulose is 1,4 beta length to 1,4 beta length to 1,4 beta length over and over and over. Do we use cellulose as fuel, as energy, or is it a building block for plants? So plants use it to store their energy, or plants use it to build their structure. It's a building block. It's a structural material that builds their I guess, existence. So would it make sense then, if you want to build something for structural stability, you want it to be stable or unstable, reactive or inert? You want it as stable and as inert as possible, meaning if everything is equatorial, is that as stable as it gets for a sugar? So would it make sense that cellulose is everything equatorial and that therefore glucose is our structural molecule? That's one that builds cellulose. Perfect. Yet it's still a sugar, so you can still get energy from it. So partially oxidized molecules can more easily be done. So now the next question, how do I know this is equatorial? So I want to steal something the way my wife teaches it that I actually think is genius. So she makes a big ordeal about the points. Is this point where these two lines meet, this carbon, is it pointing up or pointing down? Is that a point up or point down? Up. So axial is up. This point right here is down. So therefore, axial is down. So she draws the axials first, and then equatorial second. So if this is axial up, that's an equatorial down. If that's an equatorial up, that's only because that was an axial down. So how many are okay with that when drawing it? Just put your axials in first and then add your equatorials later. And yes, that means I just confessed that I married an O chemist as well. Equatorial equator, round the perimeter. Perfect. Axial on axis. Axis are straight up and straight down. So axial means on axis. Equatorial means along the equator. So does that help at least? Yeah, and they're always alternating. Equatorial is up on one, down on the other, up on one, down on the other. Alternates. Perfect. And this is the thing I hope you guys do repeatedly. Chime in the little things that help you, because yeah, I'm teaching it one way that works for me, but that doesn't work for everybody. So the more ways you think about it, and sometimes you have a question, does this work? Or sometimes like, hey, this works really well for me. So how many actually got something useful out of Stephanie's comment? Like, oh yeah, it does alternate. I remember that now. So again, I just want to say thank you for tossing these things out there because they are really helpful. And by the way, I got one private message, yes. So I'm assuming those little things help a bunch. So thank you for just little hints along the way. That said, how many also think, oh crap, that's 1, 2, 3, 4 different things I need to remember for this? Yeah, this is going to be a little bit of work, but Pyranose, 6-membered ring. So chair confirmation for Pyranoses, not for Furanoses. Okay, I'm going to erase this. Oh, okay, I don't want to touch that because you did it as a student. I've been teaching this for 30 plus years. Guess whose muscle memory is to the point where I don't even notice myself doing it anymore. Okay, I'm going to tell you an embarrassing story, which is a waste of time, and I'll still do it. So this compound is known as decalin. I realize I am socially inept because at a social function with somebody who was really cool and actually very helpful in teaching me a lot in life, and actually just somebody who's just, I admire in many ways, I sat there and told them that their kid's name was this. I am such an idiot because their kid's name is Declan. I guess it's a popular name these days. And that's all I could do is, hey, that's what this is. Okay, I'm an idiot. And my social skills are in fact 0. So, but there you go. That's how we remember things. That's known as trans Declan. Yeah, but I live in kind of an environment with lots of artsy fartsy people. This was an artsy fartsy person. This was a musician that named their kid as such. So, no, my kid is equatorial, not chair. That's so embarrassing. Yeah, this is my kid, double chair. Okay, way too much information. Okay, sadly, this is a true story. This is what I wanted for my kid's name. For middle name, I just thought middle initial of X. My wife is the one who's a sane person, so she said, no, that's just insane, and she's totally right. But I love that. Xylene would be such a cool name, but my daughter just started signing her name like this eventually, which I thought was so cool. So she would put her middle initial as that. We are such a nerdy family, too much information. What does this mean? What does 1.69 tell me? Actually, she so disappointed, my wife and I. We're both went to grad school in OChem, teach OChem or taught at like different schools. She's a biochemist. So we were very disappointed. we were like sad, and we learned to cope. We went to therapy as a family, and now we've accepted it. But yeah, I'm so kidding. We didn't go to therapy. We just yelled at her. 1.69, meaning what? Which is more favorable? This one. So here's what you need to be able to do on the test. You need to make decisions about something relative to another thing you know. So they give you this number, 1.69. For this one, first off, is it going to favor axial or equatorial for that group? What's your prediction? Oh, okay. So question was brought up. How do you know which one it favors? Generally speaking, and I should have brought this up early on, so I sincerely apologize for that. Which things bump into each other? Axials or equatorials? So which ones get crowded? Equatorial with equatorial or axial with axial? Axial bumps into each other. Axial is less stable. So the biggest thing, stereochemistry, two things bumping into each other. Equatorial is a more stable position because you don't bump into other things. So from a stereochemistry standpoint, does that seem okay? Oh, you're welcome. So for this one, first off, it's going to favor equatorial over axial, so it's going to be favorable in the forward direction. Arrows are right. But do you think the number is going to be bigger or smaller than 1.69? Okay, so got one bigger vote. So the numbers just tell me some amount of energy. And good question, what do the numbers mean? How many have no idea what this number really tells me other than it's a number? And the next one, I just need to decide, is it a bigger or smaller? Because I have no idea. 1.69 kcals per mole honestly doesn't mean anything to me. I don't know if that's a big number, small number, whatever. I just know it is a number. And apparently it's a reference number they gave me, so I must compare it to it. So which takes up more space, a carbon with 3 H's or nitrogen with 2 H's? And so two thoughts. When I move this way in the periodic table, do things get larger or smaller? The central atom gets smaller. And then which is bigger, 3 H's, 2 H's, 1 H, or 0 H's? Ah, perfect. So do you agree carbon with 3 H's is bigger than nitrogen with 2 H's, which will be bigger than 1 H, which is going to be bigger than 0 H's? So with that in mind, smaller number, perfect. So is that reasonable? I'll go with that. Okay, so it should still be a positive number, and equatorial should still be favorable. So it should be equatorial over axial, but by a smaller magnitude of number. Number of H's, it's a three-dimensional phenomenon. 3 H's is more important than carbon. Carbon is only slightly bigger than N, which is only slightly bigger. So in other words, if a fan is on and the blades are spinning, which are you worried about running into? The center of it or the spinning blades? Which one is actually taking up space and potentially going to hit you at some point? The thing spinning around it. Okay. Predict the number for this one. Just throw a number out there and see where you do. So give me a number, predict it. Perfect. Perfect. Okay. And then finally, this is a weird one. This one, kind of interesting. No, yeah, energy to break bonds are like 100 kcal, so these are way, way lower. These are just steric hindrance numbers. Okay, so sounds tempting, and this is what's kind of weird. So it's going to go back. Jonathan's question about which is more important or which you worry about hitting, the fan blades or the center. You worry about the fan blades. So if I have 3 flagpoles, you read, no big deal. But if I put flags on them, is there a chance the flags can run into each other? That flag rotates around, that flag rotates around. So which runs into each other, the flags or the flagpoles? The flags. So to answer a question which was just posted in private, perfect. So more H's and more steric hindrance. No H's, it's just a flagpole, it sticks straight up, doesn't actually run into anything. The H's create the problem, the 3-dimensional space. So give me a number here. I would immediately think carbon and nitrogen are both big, so that's going to work out. But it's actually, because it's in a straight line, surprisingly low. So you're a test writer, okay? I want you to just think about, as a test writer, is it reasonable to give somebody this number and ask for these two, or give somebody this number and ask for these two? Is that reasonable? Make people predict numbers for this, this, and this. Yeah, that's going to get you a reasonable curve. Some people will know it, some people won't. But what if you had something like this? Is this reasonable to predict, or is this a weird, oh my gosh, what just happened? So is this a, yeah, I totally get it, or is this a, huh? Without any context, this one's hard. So what are the odds that the trend would be asked here, but this one might be an exception rule? These numbers are what they are, but explain why this one's different. So in other words, as a test writer, I wouldn't predict anybody to get a trend. If I said, what is the number here given this trend, it would be random guessing. Most people wouldn't get it right. But if I were to tell you this one, seeing this trend here, this one is so different, how do you explain it? That's what you also have to recognize. They can ask questions in multiple ways. Predict based on a trend, or explain a deviation in a trend. So what are these units? That's going to be the key thing. So good question. What do these numbers represent? It's how much energy you must put into this structure when it's equatorial to convert it into axial. It's saying that this one is less stable by that amount of energy, which again, I have no idea if that's a lot or a little bit. So I'm going to have to figure these things out. So let me at least give you one thing that I'm going to make a big ordeal about. How much energy is in an H bond? How many kcals per mole? One of the things, we study H bonds all the time, and 99.99% of us can't name the energy of an H bond. We know it's there, but we don't know the numbers of it. So numbers are there just for comparison. They're not that important, but let you know, H bonds are anywhere from 4.5 to 8.5 kcals per mole. So is this more or less energy than an H bond? It's about a third or fourth or fifth. So when I talk, for instance, about a protein, when I say a protein folds, do I say it folds to maximize H bonding, or does it fold to minimize steric hindrance? It maximizes H bonding because H bonding is a lot of energy. Steric hindrance is often just an afterthought. Okay. So what key thing, CH3 is bigger than NH2, which is bigger than OH, which is bigger than CN. That's my take-home message. Erase, because that was important. So screenshot, if you will, about the, oh, okay. Yeah, exactly. It's not a deviation because you focused on less H's. So no, it's not a deviation at all. But a lot of people get it wrong because they focus on the C, the N, and the O. They see big atoms, a little bit smaller atom, a little bit smaller atom. They don't pay attention to the H's. But that's the thing. It's not a deviation, but it just didn't see. It's a linear molecule, sp hybridization. Exactly, spot on. Lines don't interfere with angles. Okay. More steric hindrance. This is just plain nomenclature. But what do you call it when the front groups on a carbon block the view of the back groups? Oh, do not memorize those values. Oh gosh, no. And that's, again, the message I want to send. There's lots and lots and lots and lots and lots of tables in my book with all sorts of numbers. Do not memorize them, but see trends when you can. Recognizing trends and data that they give you. But yeah, oh, no. This isn't this eclipse. No. This is the new moon or the twilight orientation, isn't it? I'm sorry, that's so stupid. No, it is eclipsed. Front one blocks the back one. Are these eclipsed or staggered? Oh, nobody got the terrible book series reference I just made. So one, got it. Okay. Blocked, not blocked. So I can not see them. They're eclipsed. These are known as staggered. Okay, then is there also a set of words to describe the relative positions of the CH3s? Oh man. Yeah, and it's my one out of two offspring for me just was so into that series. It was just it infected the world. Harry Potter good, Twilight not good. So helping people, being a good person, good storyline. Getting a 108-year-old boyfriend and everybody thinks it's cool, not such a good storyline. Okay, eclipsed, staggered. What do we refer to the two CH3s? I know there's words for that too, and I have to remember. Anti, far apart, perfect. This is kind of tacky. This is kind of, I don't know, kind of gauche. And these, most people don't realize they learn this word, but syn, as in syn addition, they both add in a line together. So eclipse for the overall structure, syn for the relationship, staggered and anti, and staggered and gauche. Which is the most stable conformation for minimizing steric hindrance? Anti. That's your most favorite. Ah, dang it. Let me go back. I apologize for that. I bumped it the wrong way. Okay. Most stable. And then least stable. For steric hindrance. What about if they attract? Oh, so syn means the same side. So you probably learned this. How many learned that that's known as anti-addition? On their opposite side. And how many learned this was syn addition? Do those words sound familiar from alkene chemistry? So anti-parallel, opposite of one another, and syn, synonymous addition. So exactly. So do you read suddenly when I put it here, does it look familiar in context? In here, does it look totally out of context? And the MCAT is about asking you things out of context that you know. And so your job, recognize things in a different setting, and you do great. And again, I always want to pull people's input, but how many who've taken the MCAT would agree there's a lot of things presented out of context? A lot of things that are just kind of off. Yep. And your job, recognize things in a way you're not used to seeing them. Recognize them out of context. You do better on this test. So open-mindedness and seeing the big picture really matter. Okay, I'll give you 40 seconds. Okay, let me just come clean right away. I've totally and thoroughly screwed with you. So you are right on everything we just said if we're going by steric hindrance. So I sincerely want to apologize in advance. This is not MCAT realistic. This is me being evil, mean, and getting job satisfaction out of messing with you. So here are the things you definitely did right. How many said the biggest groups are CH3, so you want them far apart? How many are okay with those? Okay, and how many said NH2 and OH are big, so far apart, NH2, so C is better? Here's where I messed with you, and I want to make a really big point of why steric hindrance is one of the more overrated things in chemistry. What holds a molecule together? H bonding or minimized steric hindrance? H bonding. So is it better to have the two groups at H bond far apart or two groups close together? You did everything right. You learned this really well. I've thrown a trick question to be mean, to make a point, not to try to make you feel bad about yourself. I apologize that the second one was follow-up from the first one, but because hydrogen bonding, really important to know this. Here's the big picture message I'm trying to send. When an enzyme forms the active site conformation, is that necessarily the most stable form, or is it the correctly aligned form? So this is one of the things that was seriously Nobel Prize winning revolutionary when people thought of it way back when in the 60s. We spent all this time looking at a protein, how it folds, but the reality is, does it have to change its orientation to allow a substrate to come on and then return to its original formation to force a substrate to react and be released as a product? So how many have heard of the phrase active site conformation? Does that sound at all familiar? So conformation refers to how this thing aligns. So it might be in this structure in one form and then rotate over for this one to align correctly to react and then return to the other one. So the take-home message, the thing I really want you to hang on to, is have to align a certain way to form an H bond to react, and then it can go back to a different conformation when it isn't H bonding. So there's my big picture. We call them conformations because they're permanent, or can they change? Does it constantly rotate from one conformation to another? It constantly changes, constantly rotates. Active site will form, do the reaction, then unform, renature to original position and release the product. Then it will form again, take on the substrate, then release, this whole concept. So I did this trick question, honestly, not to beat you up emotionally, but more to recognize the fact, can they constantly go back and forth to a hydrogen bonding stable form to a sterically favorable form, to steric here. So when it's sterically favorable, room for the substrate to come on, these two fold over, bind the substrate, carry to reaction, then they return and release. So how many are okay with that concept, that conformations are constantly changing? And that you would actually see both of these in whatever reaction you're dealing with. Okay, so hopefully that's a message being sent. Okay, couple last things I want to do on this. Isomers, just real quickly, couple words you should know. Structural isomers, also you might have learned these as constitutional isomers. Yeah, exactly. More stable because H bonding is higher energy. It's better to fold in a way to make an H bond than it is to fold in a way to get rid of steric hindrance. Okay, and conformational isomers, they follow here. Constitutional isomers, different constituents. So the easiest thing to decide whether something are structural isomers, what is the IUPAC name for this one? 5 carbons long, 5 carbons long. So I'm going to agree this is pentanol. This is pentanol. But this is 2-methyl, 3-pentanol. This is 3-methyl, 2-pentanol. How many would agree those are 2 different names? So 2-methyl, 3-pentanol. So over here is 3-methyl, 2-pentanol. Different IUPAC names, different connectivity, different structures. So these are constitutional isomers or structural isomers. Same word for the, or 2 different words for the same thing. What defines a stereoisomer? Well, these are both 1, 2, 3, 4 carbons, 1, 2, 3, 4 with an OH on 2. These are both 2-butanol. But what makes them different? They have the same connectivity. Oh, dang it. Dang it. Sorry, I'm just thumb bumping for whatever reason. Not sure why I'm fat thumbing things today so much. So for this one, how are these two different than one another? They're not perfectly superimposable. How many just learned these as optical isomers? One is R, one is S. Okay, so they have different spatial arrangement. Exactly. The CH3 matches and the ethyl group matches, but the H and OH degree are inverted. I can't put one directly on top of the other. The spots are not different. Yes, exactly. No matter how much you rotate it, twist it, or turn it, you can't get them to overlap. So even though the bonds are connected the same connectivity, the exact same bonds, they just have different alignment in space no matter what you do. They are permanently non-superimposable. Conformational isomers are temporarily non-superimposable. These are permanently non-superimposable. So one is considered R, one is considered S. Let's just do this one real quick. Priority 1 is the OH. 2 is the carbon with another carbon. 3 is a carbon with just H's. 4 is just the H. So we always go highest atomic number, number 1, lowest atomic number last. Carbon and carbon are tied, but carbon with a higher atomic number substituent. So how many learned you go draw an arrow 1, 2, 3. If 4 is in back, you just take it as is as R. Does that sound familiar? I mean, have most of you done R and S enough that it's sort of programmed in still? Okay, feeling good about this. So time to mess with you a little bit. Again, like we said, if number 4 is in back, then I can just take it as 1, 2, 3, counterclockwise, S. If number 4 is in front, what do I do? That's a little bit harder, isn't it? So what do I do if number 4 is in front? Reverse it. Exactly. Just flip it around. Just like a clock from one side, the hand's going clockwise, from the back side, it'll look counterclockwise, but it's still doing the same thing, but perfect. So 1, 2, 3 is clockwise, but because number 4 is in front, I reverse it. Okay. I think those two are easy. Where it gets tricky and where people struggle is when number 4 is in the plane. So I want you to do this. I'm going to tell you right now, this is a technique where a third of you are going to get it instantly. A third of you will get it if you do 4 or 5 practice, and a third of you are going to dislocate your elbow and fingers trying to do it, and it's never going to work. Figure out which group you're in and roll with it. But I want you to do the following. I want you to take either your right hand or left hand. I'm going to do my right hand because it's on the right side over here. I want you to put your thumb towards number 4. Okay. And then I want you to put all your fingers towards number 1. So start with your thumb towards 4. So your thumb is pointing straight up and your fingers are pointing to the right, all of your fingers. So do you agree? It's almost like you're giving a sideways high five to the molecule. Okay. Curl your fingers. So take your fingers and curl them. So in other words, your hand looks like this. And now when you curl your fingers, which hand curls towards 2? So if your hand is doing that, is that a right hand or left hand where the fingers are starting to curl backwards towards the 2, which is in back? So which hand is correctly doing that? The right hand or left hand, where the fingers start at 1 and they curl back towards 2? So that hand that's drawn there is a left hand or a right hand. So we got a right hand, left hand vote. Got another private, right hand. Okay. And apparently, right equals rectus. What's the first letter in the word rectus? If you use a right hand, it is rectus. If you use a left hand, it would be sinister. That's where the terms come from. So No, you don't always point your palms towards the page. Nope. You put your thumb towards 4 and your fingers towards 1. Because sometimes, so for instance, let's say I reverse this. Let's say this was number 2. This was number 3. Then which hand would have the fingers coming correctly? Left hand or right hand? So if I reverse 2 and 3, it would be your left hand in that case. So as I've drawn it, it's a right-handed center. Okay. This technique is useful when number 4 is in the plane. So let me give you a specific example. I want you to get these 2 chiral centers for me in terms of RNS. And this is where it gets really tricky, really challenging. So on the purple center, bromine is 1, H is 4, carbon going towards ultimately more substituted 1 is 2, that one's 3. So would your thumb be up or down in this case? Your thumb would be down in this case. So your thumb would start down. Your thumb always starts towards number 4. Your fingers would start towards 1. So which hand, a left hand or a right hand, correctly goes 1 to 2 to 3? And I'm really interested. Try it and see how quickly you get it. Okay, so for everybody who sees it right away, that's your method. It's just, if you're not getting it, we can worry about this at a later point. I'm honestly just going to say, you're getting it right away, more power to you. If you're not, I'm going to blow you off and we're going to worry about it, how we do it. And yes, so somebody asked, can I do it? I can go on camera, but here's the problem, and I run into this every time, and I'm so embarrassed, but I don't have my mirror setting right on my computer, so I don't know. You're going to have to tell me which hand it actually is. So forgive me for this one, but here it is. So which hand are you guys seeing? Left or right hand? Now I've covered up my chat box. Oh, you are seeing a left hand, because that's what it actually is. I keep on redoing my settings. I don't know. Okay, so for this one right here, I have no idea if this is going to work. But let me see. Can you, if I do my cameras just the right way, can you actually see my screen? Is this actually working? So, okay, so 1 yes. Okay, so if this is working, for this center here, I'm going to put my thumb down because it's down, and I'm going to start with my fingers towards 1, which are way over here by the bromine. So do you agree for this one, if I put my thumb down and I put my fingers out this way, does my hand look like this? How many agree with this? So you're looking at your palm. So when I curl, are my fingers coming towards you or away from you? When I curl my hand like this, coming towards, and which is sticking out? So which is in front? If I look at this is so weird. I'm having one of those weird moments. This is actually working. But how many agree this is a front carbon and that's a back carbon? So hopefully that seems okay. So with my thumb down and my fingers like this, it's coming toward. So it's coming out towards 2 before going back to 3. Okay, I don't know if that helped or not. I sure hope it did. I'm going to turn all my things back the other way. Yes, exactly. What Mo just said. The left hand is the only one that correctly curls the right way without your thumb breaking off or your fingers falling off. I hope that helped. You're very welcome. I seriously hope it helped, but I know I should go on camera for this one, but I always have my right and left all messed up. I seriously am so embarrassed by this. It's so much easier to teach this one in person because there's no camera, stuff like that. But for this one, 4. I don't know. I was on crack for a moment. 4, 3, 2, 1. So which hand is correct in this case? Oh, it's almost done. So somebody just asked how much is left. We're really, really close. Just one more thing and we're done. So this one, right-handed, so it's an R center. Perfect. Okay. So if you can do this one, and it comes with practice with your right and left hand, it just makes life easier. Okay. I'm going to exit and jump to the one last thing I want to show you. So I apologize. I just want to do R and S, and then I'm going to just blow off the question and go to, oh no, I guess I'm not blowing off the question. I'm going to this. So last thing I want to do, enantiomers and diastereomers, and then we're done. So R and S, hopefully good. Enantiomers, how many learned enantiomers are non-superposable mirror images, and diastereomers are non-superposable and not mirror images? How many were given this definition by every professor ever in every textbook ever? Straightforward, so let's see if I get it. How many are okay at seeing, if I draw a mirror right in the middle, OH reflects OH, CH3, CH3, H and back, ethyl, ethyl. So this works out really well to see a mirror and then not see a mirror. The 5-member ring reflects, the OH reflects, but CH3 does not. So if everything is drawn this way, this is a great, easy definition. I love it, except for one small problem. Is everything drawn this way, or do they draw it every which way they want? Can they mess with me by drawing it differently? So I want a slightly different definition. So help me out. If I put a left hand in the mirror, what's my reflection? So if I put one left hand in the mirror, how many agree it reflects one right hand? If I put two left hands in the mirror, it reflects two right hands. So help me out in terms of stereochem. If I put RRR in the mirror, what's the reflection? So if I put an RRR compound in the mirror, SSS, LLL, the exact opposite, exactly. Okay, what if I were to put RSS? Now I get SRR. How many agree in a reflection, every right becomes left, every left becomes right? So for an enantiomer, if they're mirror images, how many of the chiral centers have to change? None of them, some of them, or all of them? All of them, okay? Whereas if they're not mirror images, then it's some. So I'm going to totally do my definition differently. I cannot see a mirror here, but I can definitely tell you, is this chiral center the same or different? The OH one? Different, exactly. And the CH3? Different. So two chiral centers, and they're both different. So if all the chiral centers are different, they are enantiomers, because all of them reversed, which means it must have been a mirror image. Conversely, the left chiral center here, do you agree? CH3 is the same spot, the rest of the molecule same spot, but OH went from in front to in back, H went from back to in front, so that one changed. But how many agree the right chiral center is exactly the same as it was before? So this one changed. This one, same. I'm so sorry, I'm writing in such a hurry, I'm writing poorly. So is that some, none, or all that are different? Some different. So those are diastereomers. Here's where it's really helpful. I do not believe anybody on the planet can switch things in their mind and try to see a mirror image. I do not believe anybody has such amazing three-dimensional viewing ability to do that. You cannot do the mirror image approach to this one. But you can tell me this. OH is the same or different in the two structures? Different. One is axial down, the other one is equatorial up. So up and down is different. Perfect. What about chlorine? Same or different? Same thing. One's up, one's down, one's axial, one equatorial. And then finally, the methyl group, also different. So tell me what's true then. How many differ? Some, none, or all? All of them are different. So those two molecules will be classified as enantiomers. Perfect. And finally, this is foreshadowing for sugars. How many chiral centers differ from ribose to not ribose? Same, different. Only one is different. those are generically, to me as an O-chemist, diastereomers. To a biochemist, we refer to these as epimers, specifically C2 epimers. They differ at 1 chiral center in the backbone. And so that'll be something that's foreshadowing. That's for next OChem lecture. But hopefully, does that seem okay? So one last question. I swear I said we'd be done, but I want to throw one question at you, and then we truly are done. This truly is the absolute last thing. Nicely done. I'm so happy. This is seriously bringing me far more joy than it probably should. But excellent job. So I'm going to start with 1 and 2. How many changed in 1 and 2? Click too fast, dang it. So 1 and 2, same, different, different. So is that some, none, or all that are different? Some, not all. So they are diastereomers. Perfect. So 1 and 2, diastereomers. So let's see, 1 and 2 diastereomers, check. 1, 2 diastereomers, check. 1, 2 enantiomers. That answer is wrong. Okay. Next, I'm going to consider 2 and 3. So for 2 and 3, same, but different. So 2 and 3 degree differ at 1 out of 3. So those are also diastereomers because they differ just 1 out of 3. They're not different at all. So 2 and 3 are not enantiomers. 1 and 3, 1 and 3. So I can get rid of choice D because that part's wrong. Then finally, how do 1 and 3 relate? Different, different, and different. So how many agree 1 and 3? How many differ? Some, none, or all? All different. So enantiomers, just like all of you were saying. So best answer, 1 and 3 are enantiomers. How many can blow through that pretty quickly? And also, how many actually learned it that way, to look at all, some, or none? It was never taught that way. Then a few years ago, 10 years ago or so, it sort of switched. So, it's such an easy way to look at it. And it seriously, to me, enantiomers and diastereomers just destroyed people. And also, when you look at it that way, it's like, dang, mirror images, yeah, whatever. But the changing chiral centers, far easier way. Yeah, and I don't know why it wasn't taught this way before, but I will say some teachers have absorbed this as a way of teaching it, and it just makes it so much easier. The last thought, 1 and 3 have the same melting point, same boiling point, same physical properties. How many learned diastereomers have slightly different boiling points and melting points? So I could have totally worded this question differently by giving you the boiling points for all 3 or melting points, and you had to decide which one is which. So the same, and close, but slightly different, as you mentioned. Okay, sorry to make this go so much longer, but there's just a lot of stuff. And again, I really wanted to push the bio stuff on you, plus tell you the random middle name I tried to force my wife to put on a kid. That's also just as important because it's an OChem molecule. But alas, I take way too much time to make these things. You're going to enjoy it or else. Trinitrotoluene, TNT, helps you to bust out. I'm sorry that I put so much time that we're going to have to watch it or else. So this ends this. Have a wonderful day of studying. And a couple things that people brought up. How many found the amount of homework, the amount of reading for this to be excessive? It's insanely excessive. Early on, all of your work, physics, chem, bio, there's too much stuff to do at first. You're paying your dues for down the road when it gets better. It's also partly, how many of you read for lecture and it made a lot of difference, a little difference, barely any difference, no difference at all? You could have winged it. Yep. Barely any difference. And another person it helped. That's the message. The answer is going to be different for all of you, Okay. And those are the things. Whatever lesson you learned preparing for this lecture, and including the ones the last few weeks, if you're finding that you are not getting much out of the reading and the lecture is working and you can pick up everything from the lecture, then take advantage of lecture. Lecture is like a video, except you can ask questions and get feedback. Take advantage of that. Equally for them, some of you that need to review, do the review. Decide for yourself. Yeah, so unit saturation, I will go back to that one then. Yeah, and by the way, I forgot to say that. If you have any specific questions, let me go back. So I'm going to escape out of this one real quick and go back to the first question. But I guess the message still trying to send is plan your life. Don't take somebody else's schedule, modify it, make one that fits you. So the lecture matters more, lecture first, review what you need. Oh, yeah, Jonathan, I mean, you just nailed it. For me, that's exactly what I need to get. I need to see how it applies in real life and it works. Like I'm telling you, the revelation that cellulose, everything's equatorial good and stable, and cellulose good, stable building block. It's like, no, the light went on. Like that made so much sense all of a sudden. And I will never forget that everything's equatorial on glucose because glucose is used for cellulose. It's like that connection is so powerful, like those things. So the homework, I think, is it listed on the end of the very, very last page, like page 8 of the handout? It's basically passages from chapter 1 and chapter 2. Yeah, so that's your phase 1, phase 2, phase 3. Lots and lots of homework. This first chapter, tons. Yep. And yeah, so I don't know. It might match, it might not. So I go by my handout, and I'm hopeful that the portal does too. Yeah, but is it the same on the portal? And then phase 2 nitrogens? Yep. Yeah. Handout says it. Basically, he copied the handout and didn't always copy it right. Okay, so for this one. Oh, okay, so I go back. So, there's a typo on which one? Let me, unfortunately, my cursor is not working real quick. So let me, okay. So somebody who said, okay, so I will look into that. So in the handout. Oh, okay. It says C9 on the one I gave or the one from the portal? Oh, really? Okay, then okay. I'm gonna have to look at that and see how that ended up. Oh, does it really? So this should be the right answer on this one. I'm so sorry. I didn't realize. Uh-oh. Okay, so that's where the issue is. So yeah, this is definitely the right answer on this one. I will look that up. So the handout I just sent out had the wrong one. Dang it. Oh, and the answer key at the end. So the question's the same, but the answer key at the end says a C. Oh, I know what I did. I'm so apologetic. I started moving questions around because I was gonna reframe the lectures. Sorry. Yeah. So this is D. Okay, so that was why I need to go back. Okay, my apologies for that one. So, and how many use Notability or a program like that where you can just easily go in and change it on the PDF to make it correct? Okay, easily maybe is a bit of a stretch, but I mean, hopefully that works out. Yeah, so what is shown here is correct. It should be C8H11N, which is choice D. Oh, I am so utterly sorry that the first letter is off on that one. So that might be that rare case of the older handout. Okay. Oh, so it is D on the handout? Yeah. Yeah, definitely ask about that. Oh, okay. And you have the one from the portal or the one I sent? Ah. Okay. Oh, so the typo is this is a C9, not a C8. Ah, okay, then yeah, that would also be correct. Okay, so that's where the error is. Okay, I'll look at. Thank you so much. Okay, so it should be all right then. Okay, and then steric hindrance. Let me jump ahead to that. So I'm going to escape out just a second. And I prefer to go to the page that it's on just so I have writing space and it helps us to look back at what it was. Okay. And actually, thank you for catching that. I appreciate that. Okay, so the inductive effect, ask away. I know somebody mentioned it.
Yeah, do you mind if I just ask on audio?
Oh, so much
I'm
easier.
a little
Yes,
chat boxed
please.
out after 3 hours. Okay.
Yeah.
For this one, I just wanted to confirm that I got the right takeaway from this, which was that I think you were trying to compare CH3 with F3C, and then you were just saying that like because the fluorine was more electronegative, and we know that there's no lone pairs or pi bonds in this. So the fluorine is more electronegative. It's pulling electrons away from that hydrogen on the
So let me
acid.
give a totally different example. Yep. So let me give you a totally different example, and you tell me what should be true for the pKs. So basically, I have, oh shoot, sorry. I have an ethyl group. I have an ethyl with 2 fluorines that are close, and I have an ethyl with 2 fluorines that are far away. So if I told you the pK for this one equals 4.89, you tell me what you predict the pKs are for here. That hopefully, this one might be a cleaner way to look at that. And other people feel free to chime in. Yeah. Oh no. Anyway, no. But you're saying so. You expect.
I would expect that middle one to have the lowest pKa because the most electronegative F is closest to the hydrogen on the alcohol.
Okay, so if I told you this, you would say yes or no.
I would think that it should be flipped.
Okay.
Oh, yeah.
So if I told you 6.22,
I would expect this last one to be between 1 and 4, or 1.
Perfect.
8, 9.
So if I told you 1.92, something like that, exactly. So that's a trend you're seeing. And thank you. I just got a comment in the chat box. Thank you. Just positive attitude just is so powerful. So thank you for what you bring as well. So anyway, perfect. So for this one, and I don't know if these are the exact numbers, but there's a trend. So closer, greater effect, fluorine, greater effect than hydrogen. And so if you can start seeing this sort of thing where you just start just how does it compare one to the next? This is what really matters. How does it affect? So the minute you said it's going to be less than 4, check, because it's more acidic, but not as low as 1. Perfect. So does that, hopefully that seems okay. And does this sort of solidify what you were thinking?
Yeah. I was just trying to confirm that it was like the distance and the type of molecule, the electronegativity on the molecule, I should say, that's affecting it. Okay.
Perfect. Okay. And a question just came up on meso. So would anybody mind if I just erase this page and do meso on this one? It's totally unrelated to inductive effect. But meso stereochemistry question. Okay. Question on what meso compounds. Yeah, so if I have this compound, so let me do the simplest thing I can do for meso compound. And I want you to just realize your life studying for the MCAT can be summed up in a chemistry phrase. Meso inactive. I just sit around and I study all the time. I don't exercise, I don't get out, I don't have any friends. I am so inactive. Meso inactive. What does that mean? That means they are or are not optically active. They are not. If you have an R center on one side, and you have an S on the other, and they cancel. So the chiral center, H is in front, so we'll probably do 1, 2, 3, going back clockwise, but this would be your R, this would be your S. So a meso compound is simply one that has equal amounts of R and S that are perfectly symmetric, meaning my mirror image here, BRs are the same, H is the same, CH3 the same. These would be considered meso compounds. So, or this would be a meso compound, and these two are canceling centers. So a meso compound has an internal mirror plane. So what is the reflection of R? S. So RR could be meso, or RS could be meso. So which of those compounds could potentially be meso? Something RS or something RR? Only RS. Perfect. So I'm going to give you names, and without drawing structures, I want you to tell me which one is meso. So meso question mark. 2R3S, 2R3R, 2R3S, 2R3R, butane diol. Whew, sorry. Pentane diol. Pentane diol. I actually want you to do this without drawing structures. So that'll help with the logic of it. So can you at least tell me R and S wise what's going on? So can I eliminate any choices? So which of the following is meso? B and D are out. Exactly. Has B, R, and S. What's the next step in making this decision? Where would the mirror plane, even an odd number? Exactly. So if you have an even number carbon, 4, then the mirror plane degree is going to be at a number or between two numbers. Between, exactly. So it'd have to be 1, 2, 3, 4, with your mirror plane like that. That could happen. But if you're pentane, you would be 1, 2, 3, 4, 5. Your mirror plane would have to go right through it. You couldn't have a chiral center at 3. So does that help? Even though I didn't draw the structure out for these, does that make sense of like the concept of a mirror within the compound? Yeah, so why it's A over C. So R and S, that works out, that we get. But if I have 4 carbons like butane, and you agree 1 and 2 reflect 3 and 4. So why can't I draw a line of symmetry at 3 for which one? For this one or for this one? For D, well, I can because it is pentane. It is 5 carbons long. So 1, 2, 3, 4, 5. But if I tried to do this, if I did R and S, 2 problems. They're not reflecting one another. And number 2, if it's on a mirror, then you wouldn't, it couldn't be a mirror unless there's an S over here. Perfect. Okay, so cool. I guess that's MISO in a kind of numerical, mathematical perspective. And this is it in a structural perspective. So hopefully it seems okay. All right. I've been trying to stay caught up. Did I miss anybody's questions? Okay, yeah. So question about relative acidity? Sure. Okay. Well, somebody asked before. So, and right now, a lot of these things are coming in private. So 2 questions lined up. First question, reactivity or relative acidity, excuse me, in pKs. And then one more question about hydrogen bonds. So, okay, let's do the pK one first because it came in first. Okay. So specific question or just a general question about relative pK and acidity?
I guess I was just a little bit confused just about, because I think when I look at the like handout, I'm confused when it comes to like electron rich and electron withdrawing and how that relates to acidity and the pKa of it.
Okay, perfect. Then let me emphasize the bond a little bit more than I did in lecture. So I'm going to make a less of a deal about the benzene ring. Let me say something like this compared to okay. So if this is a pi bond, it's going to be electron withdrawing group. So the first atom attached has a pi bond. Is that going to ultimately then take electrons from that bond or give electrons from that bond?
Can you say that one more time?
Okay, so ultimately, what's happening to the H at the end here? Is it being given electrons or having electrons stolen from it?
Donating.
It is donated, but what's happening to it though? So here's my electron withdrawing group. So yeah, so actually that's a good way to think about it. Let's think about it this way then. So if this is electron donating on or withdrawing on one end, you're saying this H is acting like it's electron donating.
Yes, that's how I saw it.
Okay, then perfect. So let me ask you this question. If it is electron donating this way, is it going to be good or bad at donating electrons the other way?
Bad.
Right, so that means if it's a bad base, does that make it a better or worse acid?
Better acid.
Perfect. Okay, that's your way of thinking about it then. Perfect. So your way, you have the right thought. It's just I'm so busy selling you on this point over here, and you looked at something different over here. So I said this is a more like electron poor. You say electron donating group. Are we saying essentially the same thing but wording it differently?
Oh, okay. Okay, I get it.
Yeah. So you totally do get it. And therefore, and again, this is that whole point. The way a teacher says something, the way a book says something might match your concept perfectly, but it's worded different. It's okay. Word it your way. So I'm saying electron poor, you're saying electron donating. We are saying the exact same thing. And so I think that's what's going to work here. So if this is electron donating group, and I'm going to say this is going to go here, and ultimately try to push density that way. So your way then, that means this H must be an electron withdrawing group. therefore a good base, therefore a worse acid. I'm saying it's electron rich. Electron rich means it's less acidic. So perfect. I mean, and the beautiful thing, you've come up with a way to look at it that gets you a right answer, and it's all your own. So does that seem okay or seem reasonable?
I think so. I think
Now
I'm
just
looking
make the
for
decision about pKs.
a really easy, simple way to like make sure that the trend is the same for every example. So like if it's electron rich or electron withdrawing, that means it's going to be a really good base and worse acid, and then vice versa for electron donating.
Exactly. So now your job, tell me about the pK. If it's a worse acid, pK goes up or down.
Down.
So pH, if it's more acidic, pH goes up or down.
Okay, so
pH and pK. Yeah, exactly. pH and pK do the same thing, but therefore you know it. Just apply it. So better acid, pK will go
down.
Perfect. More acidic, lower pH, lower pK. Beautiful. Got it. Okay. Do you feel solid on this, or at least better than where you were?
Yes, definitely. Thank you.
Okay, then that's good. That's the big thing. Go and repeat this. Like 20 minutes from now, I want you to come up with what you just did independent.
Okay.
Okay. Another question got posed. So just another concept check. Yep. Okay. So just another concept check. If bond association energy of a bond is high, that means a bond is high energy. The energy it takes to break it is a lot. So it means to pull that, pull away. I don't want to go with electron affinity because it's slightly different. When I break a bond, am I breaking it into ions or breaking it into free radicals? So when we talk about bond association energy, when I talk about this bond breaking, am I breaking it into ions or free radicals? Exactly, radicals. They're each getting an electron. You're breaking the bond away, we each get one electron. But when you talk about electron affinity or ionization energy, are those things that make neutral free radicals, or those things that make charged species, cations and anions? They make cations and anions. So I want to be really, really careful agreeing to something like that, because sometimes that'll work out, sometimes it won't. I think you got to keep the two separate. So a stronger bond energy means they're held more tightly, so more electronegative will hold on to electrons more, but it might make one bond stronger, another one weaker. So just note that energy is just how much it holds on those electrons. And the bonds can break into ions. So it can also break, both go that way, like an acid or base, or like this free radical electron. And then how not all hydrogen bonds don't have the same strength? Oh, fairly simple to do that, I hope. So I'm going to erase this picture. So you're screenshotting 3, 2, 1, on. Which is more electronegative, N or O? O. So this has a big delta plus, this has a small delta plus. Okay. Which is a better donor? Nitrogen or oxygen? So which H bond do you think is going to be stronger? The one between the smaller delta plus with the worst donor, or the one between the bigger delta plus and better donor? Perfect. And that's why proteins fold the way they do. They always are trying to get the correctly aligned, strongest possible H bonds. It's just amazing how that works out. So why is N a better donor? Electronegativity. So which is more electronegative, O or N? O is more electronegative, perfect. So therefore O is going to pull electrons more. That's why O is a worse donor because it's less of a sharer, and is a better donor because it's more of a sharer. Less electronegative, so it's gonna donate better, and it's going to not pull as much from the H. So second option is kind of weird. Second option, like I did the extremes. H on an N to a lone pair of an O compared to H on an O to a lone pair on an N. But the better option would actually be N to N and then O to O before actually going to this one. So this is the absolute worst, this is the absolute best. And then the mix and match would be the weird one. Yeah, and the thing is with that question, I'm not going to be able to clear that up because they're not as related as it seems. So basically what it comes down to is if you want to decide how strong a bond is, two things you should consider. I'm a big believer, look at size of atoms. Shorter bonds or stronger bonds. Perfect. And then the other thought, the reason electronegativity comes into play, if O is highly electronegative, it's going to be hard to pull the electron back from it. So the bigger the electronegativity of the atom, the stronger the bond. But also the higher the electronegativity, the smaller the atom. So I would highly recommend, hugely say, stop stressing about electronegativity, ionization energy, and ionization energy, and instead focus more on bond length. Shorter bonds or stronger bonds, longer bonds or weaker bonds. Because the size of an atom follows the same trends as the other ones, and it's a cleaner, easier way to look at it. So I guarantee if you decide this is stronger because it's more electronegative, you can also decide, it's stronger because it's smaller. So my big message on this one, worry about atom size, worry about bond length more than anything else. And then, I mean, it just doesn't, for instance, which is a stronger bond, OH, SH, or selenium H? Which is a stronger bond? Strongest bond would be, that's an E, sorry. Stronger bond, shorter. When things are closer together, shorter. When I go down a periodic table, I'm meaning O, S, and SE. Yeah, you can look at it that way. I mean, I'm not going to disagree. Greater electronegativity difference, the stronger the bond, gets the same answer. O is more electronegative, so OH is going to have a bigger electronegativity difference, stronger bond, medium bond, weaker bond, but size tells me the same thing. Have a good day as well. Yeah, actually, I do apologize. I just realized I went past noon and I become the internet hog where I'm at. So I'm going to actually have to dart out as well. So, and again, sorry, lecture went over and hopefully fielded the questions were put out there. But thank you guys so much. And again, your positivity is so appreciated, especially early on and everything. And then office hours tomorrow. So I have a pretty good number of questions submitted, but I think there's probably room for a couple more still. And then I'm just going to keep checking in because I'm curious how this thing's going to be resolved. But for now, I'm going to probably just sign off then. So sorry about that. Oh, sorry, I didn't mean to click and mess that up. So.